Rogue planets. There may be more of these planets than stars in the entire galaxy. Trillions of worlds, completely dark, drifting alone through interstellar space. No sunrise, no orbit, no home star to warm them. These are rogue planets, cosmic exiles, wandering the void forever. Normally, planets form and stay close to their stars, locked into predictable orbits. But space isn't always a calm, clockwork system. A close pass from another planet, a violent gravitational tug, or even a collision can fling a planet out of its solar system entirely. Once it's out, there's no coming back. That world is doomed to roam the galaxy, unseen and alone. And they really are unseen. Rogue planets don't glow like stars. They give off no light we can spot with our eyes. Astronomers can only detect them through rare events called gravitational microlensing, where their gravity bends and magnifies the light from a background star for a brief moment. Because those events are rare, we've probably only detected a tiny fraction of the rogue planets actually out there. Why is this terrifying? Imagine if Earth were thrown into that endless night. Within days, oceans would begin to freeze. Within weeks, the air would snow down as frozen nitrogen. The planet would turn into a lifeless ice ball. There'd be no sunlight, no crops, no way to survive long term. And that kind of exile wouldn't take a supernova or alien attack. Just an unlucky nudge from a passing star could knock us out of orbit. But here's the eerie twist. Some rogue planets might not be dead at all. If they're big enough, they could keep internal heat for billions of years, with thick ice layers insulating a hidden ocean below. Entire alien ecosystems could be living in total darkness, thriving under an endless sheet of ice. That means life, strange, resilient life, could exist on a planet drifting through deep space. What makes this even creepier is the possibility that one could be near us right now. Rogue planets are almost impossible to spot until they pass very close, and their gravity could disrupt comets, pull on other planets, or even collide with something in our solar system. They are invisible bullets moving silently through the dark. Rogue planets are a reminder that even a planet's orbit, something we think of as permanent, isn't guaranteed. The universe is not a safe neighborhood. It's a place where the worlds themselves can be cast out and left to drift in the cold forever.
Blitzar Stars. There are stars out there that die twice. They collapse, go silent, and then, millions of years later, explode in one final violent flash. Astronomers call them blitzars, and they may be the source of some of the most powerful and mysterious signals we've ever detected in the universe. Here's how it works. A blitzar starts its life as an extremely dense object called a neutron star. That's the core left behind when a massive star goes supernova. Neutron stars are already extreme, just a few kilometers wide, but so dense that a teaspoon of their matter would weigh as much as a mountain. Many neutron stars spin rapidly, like cosmic tops, and that spin is the key to the Blitzar's strange story. Some neutron stars are just on the edge of being massive enough to collapse into a black hole. Normally, they'd cross that line right away, but their rapid spin creates centrifugal force that holds them up like a figure skater spinning fast enough to resist falling. For millions of years, that spin keeps the star stable. But over time, the neutron star gradually slows down, losing energy through radiation. When it slows too much, gravity finally wins. The star collapses into a black hole almost instantly. And that collapse is not quiet. Scientists think the sudden transformation produces a huge burst of energy, specifically a fast radio burst, or FRB. FRBs are incredibly brief, lasting just milliseconds, but they release as much energy as the sun produces in days or even weeks. We've detected dozens of FRBs coming from deep space, and Blitzars are one of the best explanations for what's causing at least some of them. The terrifying part is the time scale. A Blitzar could be just sitting out there, spinning quietly for millions of years, and then, without warning, it collapses and sends out a blast of energy strong enough to be detected across billions of light years. If one were close enough to Earth, it could disrupt satellites, damage electronics, or even fry parts of our atmosphere. Thankfully, most Blitzars are incredibly far away, but the universe is big, and there could be millions of neutron stars just waiting to do this. What makes Blitzars even creepier is how sudden they are. There's no brightening, no warning flare, no build-up. One moment it's a spinning neutron star, the next it's a black hole. To us, it would look like the star simply blinked out of existence. And in that blink, it would unleash one last powerful scream into the universe, a final burst of energy before vanishing forever. Blitzars remind us that even when a star seems stable, it might just be living on borrowed time. Somewhere, right now, a neutron star could be spinning down to its last seconds, ready to collapse into a black hole and send a burst of energy racing across the cosmos. We won't know until it happens, and then it'll already be over.
Fast radio bursts. Somewhere in the universe, something is sending out blindingly powerful radio signals, and we have no idea what they are. These are called fast radio bursts, or FRBs, and they might be one of the strangest mysteries in modern astronomy. An FRB is exactly what it sounds like, a quick, intense pulse of radio waves. They last for only a few milliseconds, but in that tiny fraction of a second, they release as much energy as our sun does in several days or even months. And they come from far beyond our galaxy, some of them billions of light years away. That means whatever is causing them
must be unimaginably powerful. The first FRB was discovered in 2007, almost by accident. Astronomers were combing through old data and noticed a strange one-off signal from deep space. At first, people thought it might be a mistake or interference from Earth, like a microwave oven messing with the telescope. But then, more of these bursts were found, from all over the sky. They weren't mistakes, they were real. What's terrifying is that we still don't know exactly what causes them. The leading theories include things like Blitzars, collapsing neutron stars like we just talked about, or giant flares from Magnetars, which are neutron stars with insanely strong magnetic fields. Some researchers have even speculated about exotic objects like cosmic strings, or more provocatively, advanced alien technology. That last one is unlikely, but the fact that we can't rule it out entirely keeps the mystery alive. Some FRBs happen only once, but others repeat. In 2016, scientists found the first repeating FRB, and that was a game changer. A repeating source means whatever is creating the bursts isn't being destroyed in the process. It's like a lighthouse in space, flashing again and again. That also means we can study them more carefully. And we've even been able to trace some FRBs back to the galaxies they came from. Imagine what it would feel like if one of these happened close by, close in cosmic terms anyway. The energy could overwhelm satellites, interfere with communication systems, or possibly even damage the electrical grid. Thankfully, most FRBs we've seen are so far away that they're just harmless curiosities. But the fact that they're so common means there could be nearby sources we just haven't seen yet. There's also something unsettling about the timing. FRBs don't follow any predictable schedule. They just happen. Sometimes in random bursts, sometimes in repeating patterns we don't yet understand. Somewhere, right now, an FRB is going off, and its signal is already racing through space toward us. In a few billion years, it might reach Earth, and for a split second will catch the universe screaming at us before falling silent again. FRBs are proof that there are still cosmic events we barely understand. They remind us that the universe isn't quiet. It's full of signals, explosions, and mysteries waiting to be decoded. And some of them might be stranger than anything we've imagined so far.
Gamma-ray bursts. If the universe had a doomsday weapon, this would be it. Gamma-ray bursts, GRBs, are the most violent explosions we know of, releasing more energy in a few seconds than our sun will emit in its entire lifetime. If one ever happened close enough to Earth, it could strip away our atmosphere and sterilize the planet in moments. So what exactly is a GRB? It's an intense, focused beam of gamma radiation, the highest energy form of light, fired from some of the most catastrophic events in the cosmos. Most GRBs come from the death of a massive star. When such a star runs out of fuel, its core collapses into a black hole or neutron star, and in that collapse, it launches twin jets of material at nearly the speed of light. If one of those jets happens to be aimed at Earth, we see it as a blinding flash of gamma rays. There are two main types, long GRBs and short GRBs. Long bursts last a few seconds to minutes and are linked to these massive star deaths, often accompanied by hypernova explosions. Short bursts last less than 2 seconds and usually come from something even more extreme, the collision of two neutron stars or a neutron star and a black hole. These collisions not only produce GRBs, but literally shake space-time, creating gravitational waves that we can now detect on Earth. The terrifying thing about GRBs is how much energy they unleash. In just a few seconds, a single burst can emit as much energy as hundreds of billions of suns. The beam is so focused that it's like a cosmic sniper shot. Anything in its path is toast. If Earth were in range of a GRB, even thousands of light years away, the intense radiation could destroy the ozone layer, exposing the surface to deadly ultraviolet radiation from the sun. Some scientists think a GRB might have caused one of Earth's past mass extinctions hundreds of millions of years ago. And we wouldn't even see it coming. GRBs happen unpredictably all over the universe, and the beam has to be aimed directly at us for us to notice it. That means most of them pass unseen, which is comforting and terrifying at the same time. Comforting because the odds of being hit are low. Terrifying because it could still happen at any moment, and there's absolutely nothing we could do about it. Astronomers now monitor the sky with satellites like NASA's SWIFT observation, which catch GRBs within seconds of detection. We study them not just to understand the danger, but also because they tell us about the early universe. Some GRBs come from galaxies so far away that their light has been traveling toward us for over 12 billion years, meaning we're seeing explosions from the dawn of time. Gamma-ray bursts are a reminder that space isn't just empty and peaceful. It's an arena for some of the most destructive events imaginable, and once in a while, the universe takes a shot in our direction.
Hypervelocity stars. Not everything in the galaxy moves calmly in circles. Some stars are tearing through space like bullets, traveling so fast they're on their way out of the Milky Way entirely. These are called hypervelocity stars, and they're some of the most extreme travelers in the universe. Normally, stars orbit the center of the galaxy at respectable speeds, hundreds of kilometers per second, but they still stay gravitationally bound. Hypervelocity stars are different. They're going so fast, sometimes millions of kilometers per hour, that they can escape the galaxy's gravity altogether. Imagine a star as big as the sun or bigger, just shooting off into intergalactic space, never to return. How does a star even get flung that fast? The leading explanation involves supermassive black holes, like the one in the center of our galaxy. If a pair of stars, or a star and a companion planet, pass too close to that black hole, the intense gravity can rip them apart. One object gets captured into orbit around the black hole, while the other gets hurled away at incredible speeds. It's like a cosmic slingshot, except the projectile is an entire star. There are other ways to make a hypervelocity star, too. A supernova explosion in a binary star system can kick the surviving star outward at breakneck speed. Or interactions with dense star clusters can fling one out after a series of close gravitational encounters. Whatever the cause, the result is the same: a star with enough speed to leave everything behind. The speeds are staggering. Some hypervelocity stars move at over 1,000 kilometers per second. At that pace, you could travel from Earth to the Moon in about 6 minutes. If you could somehow ride along, you'd cross the entire Milky Way in just a few million years, a blink of an eye compared to the age of the galaxy. What makes them unnerving is that they're hard to spot until they're already on their way out. Most of them are far out in the galactic halo, the outer reaches of the Milky Way, so we usually discover them only after they've been traveling for millions of years. And because they're traveling so fast, they can eventually end up in completely empty intergalactic space, burning alone for billions of years with no nearby stars or planets. It's a strange thought. Entire suns, each with their own planets, and maybe even their own life forms, ripped from their home and flung into the dark void. If Earth's sun were ever turned into a hypervelocity star, we'd be taken along for the ride, exiled from the galaxy and left wandering forever. Hypervelocity stars are reminders that even massive, stable stars can be thrown out like stones from a sling. The universe is not a peaceful, predictable place. It's a place where gravity can turn whole solar systems into intergalactic castaways.
Cosmic voids. If you think space is empty, you haven't seen a cosmic void. These are vast regions of the universe, hundreds of millions of light years across, where there's almost nothing at all. No galaxies, no stars, no glowing nebulae, just a few lonely particles scattered across incomprehensible distances. Astronomers discovered cosmic voids by mapping where galaxies actually are. When they charted the universe in 3D, they noticed something strange. Galaxies aren't spread out evenly. Instead, they form a kind of cosmic web, long filaments of galaxies and galaxy clusters, separated by huge gaps. Those gaps are the voids. A typical void can be hundreds of millions of light years wide, which is mind-bendingly huge. For scale, our entire Milky Way galaxy is about 100,000 light years across. You could line up thousands of Milky Ways inside a single void and still have room left over. These aren't just empty patches. They are the largest structures, or rather anti-structures, in the universe. The emptiness is what makes them unsettling. Even in normal space, things are pretty far apart. Stars are light years from each other. But in a cosmic void, you could travel for tens or hundreds of millions of years at the speed of light and see almost nothing. No nearby galaxies, no bright clusters, just the faintest whisper of matter left behind after the Big Bang. One of the most famous voids is the Bootes void, a staggering 330 million light-years across. It contains only a few dozen galaxies in a space where thousands would normally be expected. Some astronomers have even called it the Great Nothing.
Standing in the middle of that void, if you could, you'd see almost no galaxies in the night sky at all. Just darkness in every direction. How do voids form? They're a natural result of how matter clumped together in the early universe. Slight differences in density caused matter to flow toward certain regions, leaving others relatively empty. Over billions of years, the dense regions became galaxy clusters, while the empty regions became more and more evacuated, growing into massive voids we see today. What's eerie is that some cosmologists have wondered whether we might live in or near a void ourselves, a slightly underdense region compared to the cosmic average. If true, that could explain why we measure the expansion of the universe a little differently from some other methods. Cosmic voids are unsettling because they remind us that emptiness, not fullness, is the default state of the universe. Everything we know, galaxies, stars, planets, even life, is clumped together on thin threads of matter, surrounded by unthinkable gulfs of nothingness. Standing on Earth, we imagine the universe as full of stars, but the truth is that most of it is empty space, deep, silent, and endless. Cosmic voids are where that truth becomes overwhelming.
Dark flow. Entire galaxy clusters containing trillions of stars are moving together as if being pulled towards something beyond the edge of the visible universe. Astronomers call this phenomenon dark flow, and it might be one of the most mysterious large-scale movements we've ever discovered. Here's what we know. When scientists mapped the motion of hundreds of galaxy clusters using data from NASA's Wilkinson Microwave Aneotropy Probe, WMAP, they found something strange. The clusters weren't just drifting around randomly. They were all moving in roughly the same direction toward a point in the sky at incredibly high speeds, up to 1,000 kilometers per second. And the region they seem to be heading toward isn't anything we can see. No giant galaxy cluster, no obvious supermassive structure, no bright source of gravity. Just darkness. This is bizarre because, on the largest scales, the universe should look roughly the same in all directions. That's what we call cosmic isotropy. Galaxies should be expanding away from each other in a smooth pattern as the universe grows. But dark flow breaks that symmetry. It's as if there's some invisible mass, or maybe something stranger, tugging on entire clusters of galaxies, pulling them off course. One possible explanation is that there are massive structures beyond the edge of our observable universe, perhaps other clusters or even superclusters that we simply can't see because their light hasn't had time to reach us yet. If that's true, then the universe beyond our cosmic horizon might be very different from what we think it is. Another, more speculative idea is that dark flow could be evidence for something truly exotic, like the gravitational influence of another universe. In some versions of cosmic inflation theory, our universe is just one bubble in a multiverse. If another bubble universe is nearby, its gravity could be distorting ours and causing this flow. And here's what makes this so unnerving. Dark flow is not a slow drift. Galaxy clusters are massive, containing thousands of galaxies each, and yet they're all moving together as though something gigantic and unseen is pulling on them. That motion hasn't slowed down either. Even as the universe expands, this mysterious flow continues. Astronomers are still debating whether dark flow is real or whether it's an artifact of how we measure galaxy motions. But follow-up studies with newer data have continued to see hints of the same effect. If it is real, it might mean that our observable universe is just a tiny patch of a much larger and stranger reality. Dark flow is unsettling because it suggests that something we can't see and might never see has enough power to drag entire swaths of the cosmos along with it. Whatever's out there, it's big enough to move galaxies like chess pieces, and we're just beginning to figure out what it could be.
White holes. If black holes are the ultimate cosmic vacuum cleaners, then white holes would be their total opposite, cosmic fountains that throw matter out instead of sucking it in. The idea of a white hole sounds like science fiction, but it's a real solution to Einstein's equations of general relativity. And if they exist, they could change how we understand space, time, and maybe even the birth of our universe. A white hole is basically a black hole in reverse. A black hole's defining feature is its event horizon, a point beyond which nothing can escape, not even light. A white hole, on the other hand, would have an event horizon that nothing can enter. Instead of pulling things in, it would blast matter and energy outward. From the outside, it might look like a sudden, powerful eruption of light and particles, with no apparent source. So far, white holes are purely theoretical. We've never observed one. They pop out of the math as a kind of mirror image to black holes. In fact, some physicists think that a white hole might be what happens at the other end of a black hole, as if falling into a black hole might eventually spit you out somewhere else, maybe even in another universe, or in another universe entirely. This idea leads to some wild possibilities. Some researchers have even proposed that the Big Bang itself could have been a kind of white hole, a single, sudden eruption of matter and energy into space-time that created our universe. In that view, our entire cosmos might be the result of something that fell into a black hole in another universe. White holes are also connected to the idea of wormholes, shortcuts through space-time. A black hole on one end and a white hole on the other could theoretically form a tunnel through space. The catch? Most physicists think such a structure would be unstable and collapse almost instantly. But even if we never see one, the concept is terrifying to think about. Imagine an object appearing out of nowhere, spewing out high-energy particles or entire stars, then vanishing again. Unlike a supernova, which we can trace to a dying star, a white hole would seem to have no past, no cause, just an effect. There have even been speculations that some gamma-ray bursts or mysterious cosmic flares we observe might be white holes, briefly flickering into existence. If true, it would mean that sometimes the universe just creates matter out of nowhere, throws it around, and disappears. White holes are unsettling because they challenge the one thing we think we know about the universe, that time flows forward and causes lead to effects. A white hole would have no before, only an after. And if one suddenly appeared nearby, There's nothing we could do except watch whatever it decided to spit out into our part of the cosmos.
Quasars. Imagine a galaxy so bright that it outshines everything around it, not because of its stars, but because its heart is being devoured by a monster. That's what a quasar is, the blazing core of a distant galaxy where a supermassive black hole is feeding so violently that it lights up the entire universe. Quasars were first discovered in the 1960s as strange points of light that looked like stars. But when scientists studied their light more carefully, they realized these objects were unbelievably far away, billions of light years. That meant they had to be unimaginably powerful just to be visible to us. Some quasars are so bright they shine with the energy of 1,000 Milky Ways combined, and yet all of that light comes from a region no bigger than our solar system. So how do they work? At the center of a quasar is a black hole millions or even billions times more massive than the Sun. As gas, dust, and sometimes even whole stars fall toward the black hole, they form a swirling accretion disk that heats up to millions of degrees. The disk glows with incredible intensity, and magnetic fields can shoot out enormous jets of particles traveling near the speed of light, blasting energy across intergalactic space. What's chilling is that quasars are not rare. They were much more common in the early universe. That means billions of years ago, galaxies were actively feeding their black holes, blazing like cosmic lighthouses. If you could look back at the night sky during that time, it would be full of quasar light. Today, most quasars have quieted down as their black holes ran out of nearby fuel, but a few are still going strong. Quasars are so bright they serve as beacons, letting astronomers map the farthest reaches of the universe. They also let us peek into cosmic history, because the light we see from them has been traveling for billions of years. We're seeing them as they were when the universe was young. But they're not just beautiful, they're dangerous. The energy output from a quasar can be so intense that it strips gas from its host galaxy, shutting down star formation. In a sense, a quasar can kill its own galaxy, turning it into a place full of young stars into a quiet, dead, elliptical galaxy. If the Milky Way ever became a quasar, the radiation would sterilize huge regions of space, possibly making planets like Earth uninhabitable. Quasars are a reminder that black holes aren't just quiet traps waiting in the dark. When they feed, they can become some of the most violent and radiant objects in the universe, lighting up entire galaxies, shaping their evolution, and sending energy screaming across the cosmos.
Galactic Cannibalism. Galaxies are not peaceful islands of stars. They are predators. Out there in the universe, entire galaxies literally devour each other, tearing stars, gas, and even dark matter apart in a slow, violent feast. Astronomers call this process galactic cannibalism, and it's not rare. It's one of the main ways galaxies grow. Here's how it works. Galaxies are held together by gravity, but they're constantly moving through space. Sometimes a big galaxy and a smaller galaxy pass close enough that their gravity pulls them together. Instead of bouncing away, they merge. The larger galaxy uses its gravitational pull to rip stars and gas out of the smaller one, slowly absorbing it. Over millions or billions of years, the smaller galaxy stops being a separate object and becomes just another part of the bigger galaxy. We can actually watch this happening right now. The Andromeda Galaxy, our nearest large neighbor, has streams of stars around it, leftovers from smaller galaxies it has already consumed. And in about 4 billion years, Andromeda is coming for us. The Milky Way and Andromeda are on a collision course, and when they meet, they'll merge into a single, much larger galaxy. Most of the individual stars, including the Sun, will probably survive, but the structure of both galaxies will be completely transformed. The process is beautiful and terrifying. As galaxies merge, they create long, glowing streams of stars called tidal tails, stretching across hundreds of thousands of light years. These are like the remains of the devoured galaxy being dragged into the bigger one. Huge clouds of gas crash together, triggering bursts of new star formation, entire generations of stars born from the violence of the collision. And it's not just stars that get eaten. The supermassive black holes at the centers of both galaxies will eventually find each other and merge too, creating a single black hole even more massive than either of the originals. That event will send ripples through space-time, gravitational waves strong enough to be detected across the universe. Galactic cannibalism isn't always one-on-one either. Some giant galaxies have grown by swallowing dozens or even hundreds of smaller galaxies over their lifetimes, leaving behind a kind of cosmic graveyard of star streams and disrupted remnants. Astronomers can trace these past meals like forensic investigators, mapping the scars left behind in the galactic halo. It's a strange thought. Even galaxies are not safe from being consumed. And one day, our own galaxy will be the one doing the devouring or being devoured as we merge with Andromeda. When that happens, the night sky will be filled with spectacular, distorted arcs of stars as the two galaxies twist and tear each other apart. Galactic cannibalism is a reminder that the universe doesn't stay still. Even the grandest, most majestic structures in space are destined to collide, merge, and be remade, one cosmic meal at a time.
Zombie stars. Some stars don't stay dead. After burning through their fuel and collapsing into faint, dense embers, some of them come back to life, only to die again in one final catastrophic blast. Astronomers call these strange objects zombie stars because they rise from the grave before going out for good. Here's how it happens. When a star like our Sun runs out of fuel, it sheds its outer layers and leaves behind a dense core called a white dwarf. A white dwarf is tiny, roughly the size of Earth, but so dense that a teaspoon of its matter would weigh tons. Normally, that's the end of the story. A white dwarf slowly cools over billions of years, fading away quietly. But some white dwarfs get a second act. If they have a companion star nearby, they can start pulling matter off of it. Hydrogen from the companion star falls onto the white dwarf's surface, forming a layer that builds up over time. Eventually, there's enough material to ignite nuclear fusion again. But because the white dwarf is so dense, the fusion happens in a runaway reaction. The result is a nova, a sudden, dramatic brightening of the star as it blasts away the outer layer of accumulated gas. This doesn't destroy the white dwarf, so the process can repeat over and over as the star keeps stealing material from its neighbor. It's like a cosmic vampire feeding on another star's life to keep flaring back to life. In some cases, the white dwarf keeps feeding until it reaches a critical mass, about 1.4 times the mass of the Sun. At that point, it can no longer support itself and collapses in on itself, triggering a Type A supernova. This is one of the most powerful explosions in the universe, bright enough to outshine an entire galaxy for weeks. The white dwarf is completely destroyed in the blast, a final death, leaving nothing behind but expanding debris. Zombie stars are more than just cosmic curiosities. Type A supernovae are so consistent in their brightness that astronomers use them as standard candles to measure distances across the universe. In fact, the discovery that the universe's expansion is accelerating, the evidence for dark energy, came from studying zombie stars exploding billions of light years away. But they're also a little unnerving. A white dwarf in our own cosmic neighborhood could, in theory, reach that critical mass and detonate without warning. The blast would flood space with radiation, potentially damaging atmospheres on nearby planets. Fortunately, there aren't any known white dwarfs close enough to pose a threat to Earth, but the idea that some stars can come back after death is unsettling all the same. Zombie stars are proof that in the universe, death isn't always final. Sometimes, even a dead star gets one last, spectacular moment to go out in a blaze of glory.
Kilonovae. Some of the most precious metals on Earth, gold, platinum, uranium, may have been forged in some of the most violent collisions in the universe. These events are called kilonovae, and they happen when two neutron stars crash into each other with unimaginable force, warping space-time itself. To understand a kilonova, you have to picture what a neutron star is, the incredibly dense core left behind when a massive star explodes in a supernova. Neutron stars are tiny, only about 20 kilometers across, but they pack more mass than the Sun. Their gravity is so intense that atoms are crushed into neutrons. If you had a teaspoon of neutron star matter, it would weigh billions of tons. Now imagine two of these stellar corpses orbiting each other in a doomed dance. Over millions of years, they spiral closer and closer, losing energy as they emit gravitational waves, literal ripples in the fabric of space-time. When they finally collide, the impact is catastrophic. For a few seconds, the energy released is so great that it can briefly outshine an entire galaxy. This collision produces not just light, but heavy elements. In the chaotic aftermath, neutrons are flying everywhere, and nuclear reactions happen at a furious pace, creating elements heavier than iron, including gold, platinum, and uranium. In fact, much of the gold on Earth, including the gold in your jewelry, may have been born in a kilonova billions of years ago, before finding its way into the cloud of gas and dust that formed our solar system. Astronomers got their first real glimpse of a kilonova in 2017, when detectors on Earth picked up gravitational waves from a neutron star collision, an event called GW170817. Within seconds, telescopes around the world turned to the source and saw a fading glow, the first time we had ever seen light and gravitational waves from the same cosmic event. It was like watching the universe give us a physics lesson in real time. But there's something eerie about kilonovae, too. The violence of the collision sometimes creates a hypermassive neutron star that exists for only a few milliseconds before collapsing into a black hole. It's a reminder that even after an event that is powerful, the universe doesn't slow down. It just keeps moving on to the next stage. If a kilonova happened in our galactic neighborhood, the burst of gamma rays could damage our planet's ozone layer, potentially triggering mass extinctions. Luckily, the nearest neutron star pairs we know about are far enough away not to be an immediate danger. Kilonovae are a rare but spectacular example of cosmic destruction and creation happening at the same time. Two dead stars collide, space-time shakes, and in the chaos, new elements are born, the building blocks of planets, life, and even us. Supervoid cold spot. When scientists mapped the afterglow of the Big Bang, the faint cosmic microwave background that fills the entire universe, they expected it to look mostly smooth, with tiny fluctuations in temperature. And it did. But then they found something strange. A region much colder than the rest, a massive patch of sky that just didn't match the pattern. This is known as the cold spot, and it might be one of the most unsettling anomalies in cosmology. The cold spot covers an area of sky about 5 degrees across. That's 10 times the diameter of the full moon. It's not just slightly cooler, it's significantly colder than expected based on normal fluctuations. At first, scientists thought it might just be a statistical fluke, a rare but random fluctuation in the early universe. But then they started looking for other explanations, and things got stranger. One possible explanation is that the cold spot is caused by a supervoid, an enormous region of space that contains far fewer galaxies than average. Light passing through a region with less matter loses energy due to something called the integrated Sachs-Wolf effect. Basically, the light gets stretched by the gravitational potential as it travels through the emptier region, making it appear colder to us. The problem? The void they've found in that direction, while very large, hundreds of millions of light-years across, doesn't seem big enough to account for the entire cold spot. That has led some researchers to consider far stranger possibilities. One of those is that the cold spot could be evidence of something beyond our universe. Some cosmologists have suggested that the anomaly might be a bruise left by a collision with another bubble universe during the early moments of cosmic inflation. In other words, our universe might have bumped into another bubble universe shortly after the Big Bang, leaving behind a scar we can still see today. Even if the explanation is just a supervoid, the scale is staggering. A supervoid that large is one of the emptiest regions ever observed, containing far less matter than anywhere near us. If you could somehow stand in the middle of it, the night sky would be almost empty. Very few galaxies, very little light, just a vast expanse of nothing. Whether it's a natural feature of cosmic structure, a weird statistical anomaly, or evidence of another universe entirely, the cold spot is a reminder that the cosmos still holds secrets that defy easy explanation. Somewhere out there is a patch of space colder and emptier than almost anywhere else. A silent, frozen void staring back at us across billions of years. Spaghettification. If you ever get too close to a black hole, there's a name for what will happen to you, and it sounds almost funny. Spaghettification. But there's nothing funny about it. This is one of the most terrifying fates imaginable, and it's a very real consequence of the insane gravitational pull near a black hole. Here's how it works. Black holes have extreme tidal forces, differences in gravity over a short distance. Imagine your feet are closer to the black hole than your head. The gravity at your feet would be much stronger than the gravity at your head. As you get closer, this difference grows so extreme that it literally starts to stretch you. Your body would be pulled longer and thinner, like a piece of spaghetti, hence the name. At first, you might just feel the sensation of being stretched. But as you approach the event horizon, the point of no return, the tidal forces become so strong that they overcome the electromagnetic forces holding your body together. You wouldn't just be stretched, you'd be torn apart, atom by atom, molecule by molecule. Eventually, even the atoms themselves would be ripped apart into subatomic particles as you cross the horizon and fall into the singularity. This isn't just science fiction. It's a real, predicted effect of Einstein's general relativity. For smaller black holes, spaghettification happens outside the event horizon, so you'd be torn apart before even crossing into the black hole itself. For supermassive black holes, the tidal forces at the horizon are actually gentler. You could cross the event horizon without feeling anything at first. But as you fall deeper, you'd still meet the same fate eventually. Astronomers have actually seen hints of spaghettification happening far away in space. In 2019, they observed a star being shredded by a black hole in a process called a tidal disruption event. Over time, the star's material formed a thin stream spiraling into the black hole, just like spaghetti. The physics of spaghettification is fascinating, but terrifying. It shows how gravity, when concentrated in such a small region, can become the most destructive force in the universe. No spacecraft, no shield, no technology we can imagine could resist those tidal forces. And the scariest part? Once you're close enough, there's no way to escape. You could fire rockets at full power, but the escape velocity near a black hole exceeds the speed of light. There's no fighting it. Your fate is sealed. Spaghettification is a reminder of just how alien and deadly black holes really are. They're not just cosmic traps. They're machines that dismantle matter itself, stretching it into thin streams and swallowing it whole. If there's a worse way to die in the universe, we haven't found it yet.
Hawking radiation evaporation. Black holes are often thought of as eternal, cosmic monsters that live forever, swallowing anything unlucky enough to get close. But they're not immortal. Thanks to a discovery by physicist Stephen Hawking, we now know that black holes can very slowly lose mass over time and eventually vanish completely. This process is called Hawking radiation, and it means that even the darkest, most powerful objects in the universe have an expiration date. Here's how it works. Quantum mechanics tells us that empty space isn't really empty. It's constantly bubbling with virtual particles that pop in and out of existence in tears, a particle and its antimatter partner. Normally, they annihilate each other almost instantly. But near the event horizon of a black hole, something strange can happen. If one particle falls into the black hole while the other escapes, it's as if the black hole has lost a tiny bit of mass. Over time, this slow leakage of particles, Hawking radiation, causes the black hole to shrink. For a big black hole, this process is so slow that it's almost unnoticeable. A black hole with the mass of the Sun would take 10 to the 67 years to fully evaporate. That's a number so huge it's hard to comprehend. For comparison, the universe is currently only about 13.8 billion years old. That means the evaporation of stellar mass black holes won't even start to matter until the very distant future, long after every star in the universe has burned out. But here's where it gets really eerie. As the black hole shrinks, it radiates faster. In its final moments, it becomes extremely hot and releases an enormous burst of energy, possibly exploding in a flash of high-energy particles. The last breath of a black hole would be its brightest moment. This process has deep implications for the ultimate fate of the universe. If Hawking radiation is real, and most physicists believe it is, then eventually every black hole in the cosmos will evaporate. First the small ones, then the big ones, until even the supermassive black holes at the centers of galaxies are gone. After that, there will be nothing left but faint particles drifting in an ever-expanding, ever-cooling void. There's also a mystery here. What happens to the information that fell into the black hole? Quantum mechanics says information can't be destroyed, but if a black hole evaporates completely, where does that information go? This puzzle, known as the black hole information paradox, is one of the biggest unsolved problems in physics. Hawking radiation is chilling because it reminds us that even the most fearsome objects in the universe are temporary.
Someday, trillions upon trillions of years from now, the last black hole will release its final burst of energy and then go dark forever, leaving a universe with no stars, no galaxies, and no light.
Death of heat. If you want to know how the universe ends, the most widely accepted answer is quiet, cold, and endless. It's called the heat death of the universe, and it's not an explosion or a dramatic collapse. It's the slow fading of everything, the universe running out of usable energy until nothing happens anymore, forever. The idea comes from thermodynamics, specifically the concept of entropy, which measures disorder. Over time, energy naturally spreads out, moving from being concentrated, like in stars or galaxies, to evenly distributed. Right now, the universe is still full of places where energy flows, stars burning fuel, planets radiating heat, galaxies forming new stars. But this won't last forever. Eventually, all the stars will burn out. White dwarfs will cool into cold, dead remnants called black dwarfs. Neutron stars will fade. Even the largest, most massive stars will die. After about 10 to the 14 years, there will be no new starlight anywhere, just black holes, dead planets, and stray particles wandering the dark. But it gets worse. Over trillions of years, black holes themselves will evaporate through Hawking radiation, shrinking and finally exploding in a last flash of energy. After that, no more gravitational monsters will exist. The universe will enter what physicists call the Degenerate Era, a time when there are no stars, no black holes, just cold, diffuse matter. In this far future, particles will keep colliding, but at slower and slower rates, until eventually even matter itself may decay. Protons, the building blocks of atoms, might break apart, leaving behind only radiation and tiny subatomic particles. The universe will become a thin, cold soup of photons and leptons, spread so evenly that no structure remains. At this point, entropy will be at its maximum. There will be no energy differences left to do work, no way for anything to happen. No stars can form, no chemistry can take place, no life can survive. Time will still exist, but nothing will change. It will be an eternal, featureless darkness. This idea is terrifying, not because it's violent, but because it's inevitable. If current physics is correct, heat death is the most likely end state for the cosmos. It's the ultimate game over, not with a bang, but with an infinite stretch of silence. False vacuum collapse. Imagine waking up one day, and without warning, the entire universe ceases to exist as you know it, not in fire or explosion, but in a sudden, silent rewriting of reality itself. This is the nightmare scenario called false vacuum collapse, and it might be one of the most chilling possibilities in physics. At the heart of this idea is something called the Higgs field, the invisible field that gives particles their mass. The Higgs field is part of what makes our universe stable, but physicists have calculated that it might not be in the most stable state possible. Instead, it could be in a false vacuum, a kind of temporary energy state that isn't the true lowest energy configuration of the universe. If that's the case, then there's a possibility, however tiny, that the Higgs field could one day tunnel into its true vacuum state. If that happens, the laws of physics would change instantly everywhere. The speed of light, the masses of particles, the strength of fundamental forces, all of it could shift. Chemistry, matter, even atoms might not survive in this new reality. The truly terrifying part is that this wouldn't be a slow process. It would start at some random point in space as a tiny bubble of true vacuum, and that bubble would expand at nearly the speed of light, consuming everything in its path. There would be no warning, you wouldn't see it coming, you wouldn't feel anything. One moment the universe is as it always has been. The next moment you and everything else are rewritten or simply cease to exist. This isn't just science fiction speculation. Calculations based on the measured mass of the Higgs boson, discovered in 2012, suggest that our universe might be metastable, meaning a false vacuum collapse is theoretically possible. The good news is that the time scale for such an event is likely trillions of years or more. The bad news is that it could also happen tomorrow, and we wouldn't have any way to stop it. Some physicists think cosmic inflation, the rapid expansion that happened right after the Big Bang, might have already pushed our universe into a true vacuum state, making us safe. Others think that high-energy cosmic events, like colliding neutron stars or particle collisions, could trigger vacuum decay, though this is extremely unlikely. False vacuum collapse is one of those rare scenarios that is both scientifically grounded and existentially horrifying. It's not a question of survival, because survival would be impossible. It's a reminder that the stability of reality itself depends on a field we barely understand, and that the universe might be balanced on a knife's edge, waiting for a quantum chance to decide its fate.
Dark matter halos. Everything you see in the night sky, every star, every glowing galaxy, is just a fraction of what's really there. Most of the universe is made of something we can't see, can't touch, and can't directly detect: dark matter. And one of the most unsettling places it hides is in enormous invisible cocoons called dark matter halos that surround galaxies like our own Milky Way. Astronomers first suspected dark matter halos existed when they measured how galaxies spin. The outer stars of a galaxy orbit the center much faster than they should based on the gravity of the visible matter alone. If galaxies were made only of the stars and gas we can see, their outer regions would fly apart. Something unseen had to be holding them together. Something providing extra gravity. The solution was dark matter. And not just a little of it. In a typical galaxy, there's 5 to 10 times more dark matter than normal matter. It forms a huge, roughly spherical halo that extends far beyond the visible disk of stars.
Our own Milky Way's halo is thought to be over 1,000,000 light-years across, much larger than the galaxy itself. What makes this so eerie is that dark matter doesn't interact with light. We can't see it, can't touch it, or feel it. The only reason we know it's there is because of its gravitational pull. In other words, we're living inside an enormous, invisible structure, completely surrounded by something that passes through us constantly, and we barely understand what it is. Scientists think dark matter is made of exotic particles that don't interact with normal matter except through gravity. Billions of these particles are probably streaming through your body right now, and you don't notice at all. Experiments deep underground are trying to catch just one interaction of a dark matter particle hitting an atomic nucleus, but so far every confirmed detection has been indirect. Dark matter halos also play a critical role in the universe's structure. Without them, galaxies wouldn't have enough gravity to form in the first place. The halos act like scaffolding, pulling gas and stars together and giving galaxies their shape. Even cosmic simulations show that the universe's giant web of filaments is really a web of dark matter, with normal matter just filling in the gaps. There's an eerie comfort in knowing that dark matter is the silent skeleton of the universe, but also a chilling mystery. If we don't know what most of the mass in the cosmos actually is, how sure can we be about the future of the universe? Dark matter halos remind us that what we see is just a tiny fraction of reality. We're living inside a giant invisible cage of matter that shapes everything we know. And we still don't know exactly what we're trapped inside of. Dark energy. In the late 1990s, astronomers made a discovery so shocking that it completely changed our understanding of the universe. They found that the expansion of the universe isn't slowing down like everyone expected. It's speeding up. Something out there is pushing galaxies apart faster and faster. We call this mysterious force dark energy. And it makes up about 70% of everything in the universe. Yet we have almost no idea what it actually is. Here's how we found it. Scientists were studying Type 1a supernovae, those zombie star explosions we talked about earlier. These supernovae always shine with about the same brightness, so they're excellent cosmic distance markers, like standard candles. When astronomers compared the apparent brightness of these supernovae in very distant galaxies, they expected them to show that cosmic expansion was gradually slowing under the pull of gravity. Instead, the opposite appeared. The supernovae were dimmer than expected, meaning the galaxies were farther away than they should have been. The universe's expansion was accelerating. The simplest explanation is that there's some kind of energy built into the fabric of space itself, a cosmological constant, as Einstein once called it, that pushes everything apart. But we don't know what this energy is made of, where it came from, or why it has the value it does. It doesn't seem to dilute as the universe expands, which is what makes the acceleration continue indefinitely. The consequences are staggering. If dark energy keeps doing what it's doing, galaxies will keep getting farther apart until distant galaxies disappear entirely from view. Eventually, only the galaxies gravitationally bound to ours, like Andromeda, will remain visible. Far, far in the future, An observer in the Milky Way will look up and think they're alone in the universe, because everything else will have receded beyond the cosmic horizon. And then there are the really extreme possibilities. If dark energy gets stronger over time, the expansion could accelerate so much that eventually it overcomes all other forces, tearing apart galaxy clusters, then galaxies, then stars, then planets, and finally even atoms themselves. This is called the Big Rip, and if it's our fate, it would mark the ultimate disassembly of the cosmos. Right now, dark energy is one of the biggest mysteries in physics. We know it exists because we see its effects on cosmic expansion, but we don't know its nature. It could be a property of space itself, a dynamic field that changes over time, or even a sign that our understanding of gravity is incomplete. Dark energy is terrifying because it's everywhere, in the vacuum of space around us right now, and yet we can't touch it, can't turn it off, and can't predict exactly what it will do billions of years from now. The universe isn't just expanding, it's accelerating into a future we still don't fully understand. Rogue black holes. Most people imagine black holes sitting quietly at the centers of galaxies, far away from us. But not all black holes stay put. Some of them are wandering through the galaxy, invisible, silent, and unstoppable. These are rogue black holes, and they might be much closer than we think. Black holes form when massive stars collapse at the end of their lives, leaving behind a gravitational trap so strong that not even light can escape. Usually, these stellar mass black holes remain in roughly the same region where they were born, orbiting with other stars in the galaxy. But sometimes a black hole gets a kick, a violent push that sends it flying through space. This kick can happen during the supernova explosion that formed it, or when two black holes merge and the final burst of gravitational waves launches the new black hole away at tremendous speeds. The result is a black hole traveling on its own path through the galaxy, not tied to any star system. And here's the terrifying part. Rogue black holes are essentially invisible. They emit no light of their own. The only way we can detect one is by the way its gravity bends the light of stars behind it, a phenomenon called gravitational microlensing, or by the faint X-rays it produces if it happens to pass through a cloud of gas and start feeding. Otherwise, a rogue black hole could be drifting right past us and we'd never know. Astronomers estimate there could be hundreds of millions of black holes in the Milky Way, many of them unaccounted for, and some likely traveling through interstellar space alone. In 2022, scientists confirmed the detection of a single isolated black hole about 5,000 light-years away, proof that rogue black holes really do exist. If one wandered too close to our solar system, the results could be catastrophic. It wouldn't have to swallow Earth directly to cause trouble. Its gravity could disrupt the orbits of planets, fling comets from the Oort cloud toward the inner solar system, or destabilize entire star systems. Even a distant pass could dramatically change the architecture of our cosmic neighborhood. Thankfully, the odds of a rogue black hole passing dangerously close to us are low, but not zero. The Milky Way is a big place, but these objects have billions of years to roam. The thought that one could silently creep toward us, unseen, until its effects become obvious, is one of the more chilling possibilities in astronomy. Rogue black holes are the ultimate stealth danger, massive, unstoppable, and dark. They remind us that even when space seems empty, there may be invisible giants wandering the night, carrying the power to reshape entire solar systems without warning.
Venus's atmosphere. If you want to know what hell might look like, just look at Venus. Our sister planet may be close to Earth in size, but its atmosphere is one of the most hostile environments in the entire solar system. A place where the air is thick enough to crush metal, and the rain is literally made of acid. Venus is wrapped in a dense atmosphere of carbon dioxide, about 96% CO2, with a small amount of nitrogen. That atmosphere is almost 100 times thicker than Earth's, meaning if you stood on the surface, you'd feel the pressure of being nearly a kilometer under the ocean. Any human visitor or any unprotected machine would be crushed in seconds. But the pressure is only part of the nightmare. The thick atmosphere traps heat through an extreme greenhouse effect, turning Venus into the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The surface temperature averages around 465 degrees Celsius, 870 degrees Fahrenheit, hot enough to melt lead, zinc, and many metals we use in spacecraft. That heat is constant, day or night, pole or equator. The clouds above Venus are made mostly of sulfuric acid droplets, forming thick, yellowish layers that completely block our view of the surface in visible light. While the acid doesn't quite reach the ground, it evaporates before hitting the surface due to the extreme heat. The upper atmosphere is filled with corrosive chemicals that would destroy electronics and spacecraft coatings in hours. We know this because we've tried to visit. Soviet Venera probes in the 1970s and 1980s were the first to land on Venus. They survived for as little as 23 minutes and as long as about 2 hours before the crushing pressure, scorching heat, and chemical assault destroyed them. Some of the images they sent back show a barren, cracked landscape under a dim orange sky, one of the most hostile places we've ever seen. Even the wind patterns are eerie. High above the surface, winds rage at hurricane speeds, whipping the planet's clouds around in just a few days. But near the surface, the air moves sluggishly, so slowly that it would take a breeze minutes just to move a few inches. The entire planet seems locked in a suffocating stillness beneath its boiling sky. Venus's atmosphere is a stark warning of what happens when a planet's climate runs away. Billions of years ago, Venus might have had oceans and a milder climate, but a runaway greenhouse effect boiled the oceans away, and the planet became the furnace we see today. Standing on Venus would mean crushing weight on your chest, burning heat on your skin, and an unbreathable, toxic atmosphere. It's not just inhospitable, it's actively hostile to life, a true planetary nightmare hiding behind a bright, beautiful evening star.
Io's lava lakes. If Earth's volcanoes seem dramatic, they're nothing compared to what's happening on Io, one of Jupiter's largest moons. Io is the most volcanically active world in the entire solar system, a place where lava lakes bubble constantly. Sulfur plumes shoot hundreds of kilometers into space, and the surface is being endlessly reshaped by eruptions. Io's surface looks almost alien. Instead of oceans or continents, it's covered with bright yellows, reds, and oranges, the colors of sulfur compounds deposited by volcanic activity. You can see massive calderas and lakes of molten rock glowing red-hot, some hundreds of kilometers across. The volcano Loki Patera, for example, is so huge and active that it alone produces more heat than all of Earth's volcanoes combined. So why is Io so violent? The answer is tidal heating. Io is locked in a gravitational tug-of-war with Jupiter and the other large moons, Europa and Ganymede. As Io orbits Jupiter, the giant planet's gravity stretches and squeezes Io over and over again. This constant flexing generates enormous amounts of internal friction and heat, enough to melt rock inside the moon. The result is a molten interior that constantly seeks to escape, producing nearly continuous volcanic eruptions. Some of Io's eruptions are so powerful that they're visible from space telescopes. NASA's Galileo spacecraft, which studied the Jovian system in the 1990s, observed plumes rising up to 500 kilometers high, blasting material into space and creating a thin, patchy atmosphere around the moon. Imagine standing there, the ground beneath your feet trembling, fountains of molten sulfur shooting toward the sky, and a massive planet filling half the horizon. Io's lava lakes aren't just hot. They're some of the hottest surfaces outside the sun itself, reaching temperatures above 1,600 degrees Celsius. The surface is constantly changing as lava flows cool and new eruptions cover old ones. If you visited Io twice a year apart, the landscape would look noticeably different. But Io is not a friendly place. Besides the constant threat of lava, it's deep inside Jupiter's intense radiation belts. Any unshielded human or spacecraft would be bombarded with lethal doses of radiation within minutes. Combined with its volcanic activity, Io might be one of the most dangerous places a human could ever try to stand. Studying Io is more than just curiosity. It helps us understand how tidal heating works and how it might affect other worlds, even exoplanets orbiting distant stars. Io is a reminder that moons can be just as geologically alive and just as hostile as planets. Io's entire surface is a battlefield of fire, torn open and remade again and again. It's not a dead rock orbiting a planet. It's a world in constant eruption, a place where the ground never truly rests.
Europa's hidden ocean. Beneath the icy surface of Europa, one of Jupiter's largest moons, there may be a vast global ocean, and it could be one of the most likely places to find alien life in our solar system. Europa looks cold and quiet from the outside, just a smooth, cracked shell of ice, but underneath there might be more water than all of Earth's oceans combined. Scientists first suspected an ocean when they studied images from NASA's Galileo spacecraft in the 1990s. Europa's surface is covered with strange ridges and broken patterns, as though the ice has been fractured and shifted repeatedly. That suggests the ice is floating on a liquid layer, allowing the crust to crack and move. More recently, the Hubble Space Telescope and other instruments have detected what appear to be plumes of water vapor shooting into space, possible vents from the hidden ocean below. How could liquid water exist so far from the sun, where the temperature is around minus 160 degrees Celsius? The answer is tidal heating. Just like Io, Europa is constantly pulled and flexed by Jupiter's immense gravity, and that flexing creates heat inside the moon. That heat is enough to keep water beneath the surface from freezing solid, creating a salty global ocean locked under kilometers of ice. This ocean could be 100 kilometers deep, dwarfing Earth's oceans. And here's where it gets really fascinating and a little terrifying. Where there's liquid water, there could be life. On Earth, we find life thriving around deep ocean hydrothermal vents, completely cut off from sunlight. These ecosystems are powered by chemical energy, not photosynthesis. If similar vents exist on Europa's ocean floor, they could provide a stable energy source for alien organisms. But we have no idea what might be down there. It could be simple microbial life, or it could be something more complex. Alien equivalents of fish, squid, or even larger predators that have evolved in total darkness over billions of years. Whatever is in that ocean has never seen sunlight, never experienced seasons, and lives in a completely sealed environment. Europa has become one of the top targets for future exploration. NASA's Europa Clipper mission, launching soon, will fly by the moon multiple times to map its surface and search for signs of habitability. One day, we may even send a probe to drill through the ice and explore the ocean directly. The thought of being the first to glimpse life in that alien sea is thrilling, but also unsettling. Europa's ocean is a place where we might not be at the top of the food chain. In the black, pressurized depths of that world, anything could have evolved, and we won't know until we go there and look.
Titan's methane lakes. If you want to visit one of the strangest places in the solar system, look no further than Titan, Saturn's largest moon. Titan is the only other world we know of with stable liquids on its surface, but instead of water, its lakes and seas are made of liquid methane and ethane, and they lie under a thick, hazy orange sky. Titan is almost like an alien version of Earth. It has rivers, lakes, seas, and even rain, but the temperatures are so cold that water is frozen as hard as rock. Instead, methane and ethane take water's place in Titan's weather cycle. Methane evaporates into the atmosphere, forms clouds, rains down, and fills rivers and seas. To stand on Titan's shore would be to watch waves of liquid methane lapping against a beach made of solid water ice. The largest seas on Titan are truly enormous. Krakenmeer, the biggest, is thought to be roughly the size of the Caspian Sea on Earth. Some of Titan's lakes are hundreds of meters deep. If you fell in, you wouldn't drown right away. Methane is less dense than water, but you'd quickly freeze in the minus 179 degrees centigrade temperatures. Titan's atmosphere is thick, denser than Earth's, and filled with nitrogen, with a mix of methane giving it its orange color. That haze blocks much of the sunlight, so standing on Titan would feel like standing under an endless dim twilight sky. The air pressure is similar to what you'd feel 15 feet underwater on Earth, so a human could technically survive without a pressure suit, but you'd need oxygen and serious protection from the cold. The eeriest part is that Titan may hide even more secrets below the surface. Beneath the crust of ice, scientists believe there could be a vast subsurface ocean of salty water, meaning Titan might have two separate oceans, one of methane on the surface and one of water below. If that's true, Titan might be one of the most promising places for alien life in the solar system, especially if there are hydrothermal vents on the ocean floor, similar to Europa. NASA's Cassini spacecraft spent years studying Titan, even dropping a lander called Huygens in 2005, which gave us our first close-up view of the surface. Future missions, like NASA's Dragonfly drone, will actually fly through the thick Titan atmosphere, hopping between sites and exploring its chemistry, and maybe even its methane seas. Titan's lakes are haunting because they're so familiar, yet so alien. They mimic Earth's landscapes, but with an entirely different chemistry. If you stood on a methane shoreline under that orange sky, you'd be looking at one of the most surreal vistas in the solar system, a frozen world where it rains methane and rivers carve their way through a landscape of ice.
Neutron Star Mountains. On Earth, a mountain can rise kilometers into the sky. On a neutron star, a mountain would barely rise a millimeter, and yet it could weigh as much as Mount Everest. These tiny, impossibly dense mountains are some of the strangest and most extreme features in the universe. First, let's talk about what a neutron star is. When a massive star dies in a supernova, its core collapses under gravity until the protons and electrons are crushed together to form neutrons. The result is an object only about 20 kilometers wide, but with more mass than the Sun. The density is unimaginable. A teaspoon of neutron star matter would weigh billions of tons. Because neutron stars are so dense, their gravity is insanely strong, about 100 billion times stronger than Earth's. That means their surfaces are almost perfectly smooth. Anything sticking out would be crushed flat, unless it's supported by the star's intense crust, which is made of some of the strongest material known to physics. That's why neutron star mountains are so tiny. They can only rise a few millimeters high before gravity pulls them back down. And yet, those millimeters of material weigh as much as the tallest mountains on Earth. Think about that. A bump the size of a grain of sand on a neutron star could weigh more than an entire mountain range here. These mountains aren't just theoretical curiosities. They may have profound effects on what we observe from neutron stars. As the star spins, those tiny bumps create slight irregularities in its gravitational field, producing ripples in space-time called gravitational waves. Detecting these waves could give astronomers clues about what neutron stars are made of and how strong their crusts really are. The existence of neutron star mountains also tells us something about just how exotic these stars are. The crust must be strong enough to hold them up against mind-crushing gravity, likely made of a lattice of super-dense nuclei that behaves like a single solid object. Computer simulations suggest this material could be 10 billion times stronger than steel, making neutron star crust the toughest material in the universe. And here's an eerie thought. Neutron stars sometimes glitch, suddenly changing their spin rate, possibly because these tiny bumps crack and rearrange under stress. Imagine an entire star quaking because its surface mountain shifted, a stellar-scale earthquake caused by bumps smaller than your fingernail. Neutron star mountains are a reminder that scale in the universe can be completely counterintuitive. Something barely tall enough to measure with a ruler can have the weight of a planet, and its collapse can send gravitational shivers across the galaxy. On a neutron star, even the smallest features carry cosmic significance and cosmic mass.
Exoplanet WASP-76b. If you thought acid rain was bad, imagine living on a world where it rains molten iron. That's the bizarre reality of WASP-76b, a distant exoplanet that has some of the most extreme weather ever discovered. WASP-76b is a type of world called a hot Jupiter, a gas giant like Jupiter, but orbiting extremely close to its star, so close that a year lasts less than 2 days. Because it's tidally locked, one side of the planet is in perpetual daylight, while the other is trapped in eternal night. This creates a planet-wide nightmare of scorching heat, wild winds, and iron rain. On the day side, temperatures soar to around 2,400 degrees Celsius, or 4,300 degrees Fahrenheit, hot enough to vaporize metals like iron. In fact, iron on the day side doesn't stay solid at all. It becomes gas, mixing into the atmosphere. Winds then carry this vapor toward the night side, where it cools and condenses back into liquid iron, falling as a deadly rain. This means that on WASP-76b, you could theoretically stand under a metal storm, though you wouldn't survive long enough to appreciate it. The planet's atmosphere is scorching and toxic, and the winds that transport the vapor blow up thousands of kilometers per hour, creating a constant, planet-wide storm. Astronomers discovered this strange weather pattern by using powerful telescopes to analyze the starlight passing through WASP-76b's atmosphere. They detected the spectral fingerprints of iron on the day side, but none on the night side, implying that the iron must be condensing and literally raining out of the atmosphere. the planet's proximity to its star makes it one of the most hostile places we've ever studied. The star's radiation blasts the planet so intensely that the atmosphere is likely puffed up and slowly evaporating into space. Over billions of years, WASP-76b may actually lose a significant fraction of its mass. Even the sky would be alien. On the day side, there's no blue. The light would be a blinding white-yellow glare, hotter than the hottest furnace on Earth. On the night side, you might see glowing clouds of metal vapor and flashes of lightning from storms driven by extreme temperature differences. And somewhere above, droplets of iron would be falling, cooling into glowing beads before splattering onto the atmosphere's lower layers. WASP-76b is a reminder that not all planets are remotely hospitable. Some are truly alien, with conditions that sound like something out of a nightmare. And there are probably countless worlds, even stranger than this one, waiting to be discovered. In the search for other planets, WASP-76b stands out as a warning. Not every world out there is a potential home. Some are more like cosmic furnaces, where even the rain could melt through you in seconds.
55 Cancri E. Imagine a planet made partly of diamond. A world that glitters beneath the light of its star. That's what scientists think might be true for 55 Cancri E, one of the most exotic exoplanets we've ever discovered. But don't get too excited. This is no paradise. It's an extreme, hellish world with scorching heat that makes it completely uninhabitable. 55 Cancri E orbits a star just 40 light-years away in a system with several known planets. It's what astronomers call a super-Earth, about twice the size of our planet and 8 times as massive. But what makes it truly fascinating is its composition. Based on its density and the chemical makeup of its host star, researchers believe 55 Cancri E could have a huge amount of carbon, so much, in fact, that a large fraction of the planet might exist in the form of diamond deep below the surface. If that's true, this would make 55 Cancri E a diamond planet, its crust and mantle potentially full of carbon-rich minerals compressed into glittering crystals under intense pressure. The value of such a planet would be beyond comprehension, a literal world of precious material. But before you start dreaming about interstellar mining, here's the catch. 55 Cancri E is not a friendly place. It's tidally locked, meaning one side always faces its star and is in constant daylight, while the other is in perpetual night. The day side is blasted with intense radiation, pushing temperatures to over 2,000 degrees Celsius, hot enough to melt rock. Any atmosphere it might have would be a toxic soup of carbon dioxide and carbon monoxide, and possibly vaporized minerals. Recent studies suggest that the planet may even have lava flows or a global ocean of molten rock on its star-facing side. The extreme heat could cause parts of the surface to literally glow. If you stood there, somehow surviving the heat, you might see the horizon shimmering with incandescent magma under a sky filled with poisonous gas. What's even more unsettling is how close the planet is to its star. 55 Cancri E orbits so near that its year is less than 18 hours long, meaning you could watch an entire orbit in a single Earth day. Its proximity also means it's slowly spiraling inward due to tidal interactions, and one day it may be torn apart by its star's gravity. 55 Cancri E is a reminder that not every beautiful idea in astronomy is safe or welcoming. A planet made of diamond sounds like treasure, but in reality, it's a fiery, toxic nightmare where nothing we know could survive. It's a cosmic jewel locked in a furnace, glittering, deadly, and forever out of reach.
TRAPPIST-1e Tidal Lock. Imagine a world where the sun never rises or never sets. That's the reality of TRAPPIST-1e, one of 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1. This planet is tidally locked, meaning the same side always faces its star. One hemisphere is in eternal daylight, scorching under constant sunlight, while the other is trapped in an endless frozen night. TRAPPIST-1e is part of a remarkable planetary system about 40 light-years away. Because its star is much cooler and dimmer than our Sun, TRAPPIST-1e lies within the so-called habitable zone, where temperatures could allow liquid water to exist. That has made it one of the most exciting targets in the search for alien life. But tidal locking makes the environment far stranger and potentially much more extreme than Earth's. On the day side, the constant light could create intense heating, possibly evaporating water and driving violent winds that rush toward the dark side. On the night side, the lack of sunlight could cause temperatures to plummet so low that the atmosphere might even freeze out. If you stood on the day side, you would see the star fixed permanently overhead. No sunrise, no sunset, just an unchanging sky. On the night side, you'd never see the star at all. Only a pitch-black sky filled with distant stars. The most interesting region might be the Terminator line, the twilight zone, where day meets night. Here, temperatures might be just right for liquid water, making it the most habitable strip of land on the entire planet. If life exists on TRAPPIST-1e, it might be confined to this thin band, evolving under permanent sunset skies. Scientists are fascinated by what tidal locking means for a planet's weather and habitability. The atmosphere could circulate heat from the day side to the night side, softening the extremes. But if the atmosphere is too thin, the night side might become so cold that gases freeze and fall to the ground, collapsing the atmosphere entirely. Even if TRAPPIST-1e is habitable, it would feel eerie to live there. Imagine growing up under a sky that never changes, where shadows never move, and the concept of time of day doesn't exist. Travelers could walk from blazing hot daylight into a freezing eternal night just by crossing the planet's surface. TRAPPIST-1e reminds us that habitable doesn't mean comfortable. A world with endless day and endless night would be a strange place to call home. One where survival might depend on living forever in twilight. It's both hopeful and haunting to imagine that somewhere out there, life might already be thriving under a sky that never changes.
Hot Jupiters. Gas giants aren't always distant cold worlds like Jupiter and Saturn. Some of them orbit so close to their stars that they're practically skimming the stellar surface. These worlds are called hot Jupiters, and they are some of the strangest, most extreme exoplanets ever discovered. Giant planets so hot they may literally be vaporizing into space. Hot Jupiters were among the very first exoplanets astronomers found. In 1995, scientists detected 51 Pegasi b, a planet about half the mass of Jupiter, but orbiting its star once every 4 days. That discovery shocked astronomers. Nobody expected gas giants to be that close to their stars. Since then, we've found hundreds more, and they defy almost everything we thought we knew about planetary systems. A typical hot Jupiter is massive, similar to Jupiter or larger, but its orbit is extremely tight, sometimes less than 0.05 astronomical units from its star. That's only a few million miles away. For comparison, Mercury, the closest planet to our Sun, is nearly 58 million kilometers away, or 36 million miles away. These planets are so close that their atmospheres are superheated to 1,000 degrees Celsius, or 1,800 degrees Fahrenheit. The heat can cause some truly bizarre effects. Some hot Jupiters are puffed up, swollen to enormous sizes as their atmospheres expand. Others are being stripped apart by their stars, leaving behind comet-like tails of gas trailing in their orbits. Over millions of years, some of these planets could lose so much material that they shrink into something closer to a rocky core, the bare remnant of a once mighty gas giant. Hot Jupiters are also tidally locked, meaning one side is always facing the star, just like the moon faces Earth. This creates an extreme day side and night side with wild temperature differences that can drive supersonic winds, up to 5,000 miles per hour, that move heat and material from one hemisphere to the other. And if the idea of a planet evaporating isn't eerie enough, some of these worlds might even have metal rain. On certain hot Jupiters, astronomers have detected vaporized metals in the atmosphere, which could condense and rain down on the night side. Imagine a world where droplets of molten iron or titanium fall from the sky while the entire horizon glows with reflected starlight. Hot Jupiters are unsettling because they break our expectations. They're giants that don't live in the distant, icy outskirts, but in the furnace next to their stars.
They remind us that planetary systems can form in ways we never imagined, and that some worlds are doomed to be slowly cooked away, one layer at a time. If Jupiter were as close to the Sun as a hot Jupiter is to its star, it would dominate the sky, a massive, boiling planet that might not last long enough to be admired. Hot Jupiters are cosmic warnings that even planets can get too close to the fire.
Planetary quakes on Mars. For a long time, scientists thought Mars was a geologically dead world, a cold, silent desert where nothing moved except dust storms. But recent discoveries have revealed something surprising. Mars is still alive, geologically speaking. The planet shakes with its own version of earthquakes, called Marsquakes, and some of them are powerful enough to reshape its surface. The breakthrough came from NASA's InSight lander, which touched down on Mars in 2018. InSight carried a highly sensitive seismometer designed to listen for vibrations in the Martian ground. Almost immediately, it began detecting tiny tremors, proof that Mars is still active inside. Over the course of its mission, InSight detected thousands of Mars quakes, some of them surprisingly strong, with magnitudes over 4. These quakes don't happen the same way they do on Earth. Mars doesn't have plate tectonics. Its crust isn't broken into moving plates that slide past each other like ours. Instead, Mars quakes seem to come from the slow cooling and contracting of the planet's interior. As Mars cools, its crust shrinks and cracks, releasing stress in sudden jolts that shake the surface. Some of the strongest Mars quakes came from a region called Cerberus Fossae, a system of long, deep fissures stretching across the Martian surface. This area may still be volcanically active, which is astonishing because Mars was thought to have lost most of its volcanic activity billions of years ago. The fact that it still has hotspots suggests the planet's interior isn't completely dormant. There could still be magma chambers lurking below. These quakes are more than just a curiosity. They can reshape the landscape over time, triggering landslides, collapsing lava tubes, and opening new fractures. They also tell scientists about Mars's internal structure. By studying how seismic waves travel through the planet, researchers have learned about the size of Mars's core and the composition of its crust and mantle. But Marsquakes could also pose a hazard for future explorers. Imagine building a base on Mars and waking up to feel the ground trembling beneath you. A large quake could destabilize structures, shift rocks, or even trigger dust avalanches down nearby cliffs. Since Mars doesn't have a thick atmosphere to dampen vibrations, the shaking might feel sharper and last longer than what we're used to on Earth. Perhaps most intriguingly, these quakes hint that Mars may not be as dead as we thought. If there is still volcanic activity deep underground, there could be geothermal heat. And where there's heat, there might be liquid water trapped beneath the surface. That could be a potential habitat for microbial life.
Mars is a world that looks quiet from orbit, but its quakes reveal it's still restless, still evolving. The red planet is not a frozen relic of the past. It's still shifting and cracking, as though reminding us that it hasn't completely gone cold yet.
Neutron stars. Imagine compressing an entire star into something the size of a city, and then holding a teaspoon of that material in your hand. That tiny spoonful would weigh as much as a mountain. This isn't science fiction. It's the reality of neutron stars, some of the strangest and most extreme objects in the universe. Neutron stars are born in catastrophe. When a massive star reaches the end of its life, it explodes in a supernova, blasting its outer layers into space. What's left behind is the collapsed core, crushed under gravity until the protons and electrons combine into neutrons. The result is a sphere only about 20 kilometers wide, roughly the size of a city, but with more mass than the Sun. The density is almost impossible to comprehend. A single cubic centimeter, about the size of a sugar cube, would weigh hundreds of millions of tons on Earth. The matter inside a neutron star is packed so tightly that atoms don't even exist in their usual form. Instead, you have a sea of neutrons behaving like one giant atomic nucleus. Neutron stars also spin incredibly fast. Some rotate dozens or even hundreds of times per second, flashing beams of radiation like cosmic lighthouses. We call those pulsars, and their rhythmic pulses are so regular they rival atomic clocks in precision. Their magnetic fields are another level of extreme. The most magnetic neutron stars, called Magnetars, have fields trillions of times stronger than Earth's. A Magnetar's magnetic field could literally erase credit cards from thousands of kilometers away, and close to the surface, it could rip electrons off atoms. If you could somehow stand on the surface of a neutron star, which you can't, you'd be crushed instantly. The gravity would be about 100 billion times stronger than Earth's. That means if you somehow jumped, you'd fall back down so fast you'd hit the ground at a significant fraction of the speed of light. Even light itself bends significantly near a neutron star, distorting how we see them. And then there are neutron star collisions, events so violent that they send ripples through space-time that we can detect on Earth. These mergers produce kilonovae, create heavy elements like gold and platinum, and may leave behind black holes. Neutron stars are fascinating, but also deeply unsettling, because they represent a kind of matter we can't reproduce on Earth. They are nature's densest laboratories, places where the known laws of physics are pushed to their limits, and maybe even break down. Looking at a neutron star is like looking at the bones of a dead star, compressed into a cosmic tombstone, spinning endlessly in space. They are beautiful in their strangeness and terrifying in their sheer, crushing power. Magnetars. If neutron stars are already extreme,
Magnetars are their even more terrifying cousins. These are neutron stars with magnetic fields so powerful they defy comprehension. Trillions of times stronger than Earth's magnetic field. If a magnetar were somehow placed halfway across our solar system, it could still wipe the data on every credit card on Earth. That's how intense its magnetic field is. Magnetars are born the same way as ordinary neutron stars, in the explosive death of a massive star. But for reasons scientists are still working to understand, some of these collapsed cores are left spinning with such incredible speed and with so much magnetic energy that they become the most magnetic objects in the universe. The magnetic field of a magnetar is so strong it actually changes the rules of physics nearby. It can distort the shapes of atoms, turning them into long, thin cylinders. If you could get close, which you wouldn't survive, the field could literally pull the electrons off the atoms in your body. It's not just deadly. It's a kind of destruction that happens at the atomic level. Magnetars don't just sit quietly either. They're known for producing sudden, violent bursts of energy called giant flares. In 2004, one magnetar in our galaxy, called SGR 1806-20, released a flare so powerful it briefly altered Earth's ionosphere from 50,000 light-years away. If a flare like that went off within a few dozen light-years, it could strip away parts of our atmosphere and fry satellites. Most magnetars are relatively short-lived in cosmic terms. Their magnetic fields decay over about 10,000 years, which is just a blink of an eye for a star. As they lose magnetic energy, they become more like ordinary neutron stars. But while they're active, they are some of the most dangerous objects in the universe. We can detect magnetars by the X-rays and gamma rays they emit, as well as their occasional outbursts that light up space. They may even be responsible for some of the mysterious fast radio bursts, FRBs, we've detected from distant galaxies. A quick, powerful signal coming from an object that's essentially a cosmic magnetic bomb. What makes magnetars particularly eerie is how rare and unpredictable they are. We know of only about 30 in the entire Milky Way, but there could be thousands hiding in the galaxy, quiet and waiting to erupt again. Magnetars are a reminder that even after a star dies, it can leave behind something incredibly dangerous. They are like ticking cosmic grenades, dense, small, and capable of unleashing bursts of energy that could devastate a star system. And somewhere out there, dozens more may be waiting to flare again.
Pulsar beams. Somewhere in the galaxy, there are dead stars spinning so fast they act like cosmic lighthouses, sweeping beams of deadly radiation across space with every rotation. These are pulsars, one of the most fascinating and frightening types of neutron stars. A pulsar is born when a massive star explodes in a supernova, leaving behind a neutron star, an object only about 20 kilometers across, but more massive than the Sun.
Some neutron stars spin incredibly fast, completing dozens or even hundreds of rotations per second. As they spin, they generate powerful magnetic fields that funnel charged particles toward their magnetic poles. These particles emit beams of radio waves, X-rays, or gamma rays that shoot into space. If one of those beams happens to sweep across Earth, we see it as a regular pulse of radiation, hence the name pulsar. Some pulsars are so precise they rival atomic clocks, flashing with perfect regularity for millions of years. But as fascinating as they are, pulsars aren't gentle. Those beams are extremely energetic, capable of sterilizing anything caught in their path. Imagine being on a planet orbiting a pulsar. If the beam hits, the radiation would strip away your atmosphere, fry any surface life, and leave the planet a barren wasteland. Even a glancing exposure to that much high-energy radiation would be catastrophic for living things. This is why most pulsar planets, and yes, astronomers have discovered planets orbiting pulsars, are unlikely to be habitable. Some pulsars are even more extreme. Millisecond pulsars spin hundreds of times per second, blasting space with rapid-fire radiation. Others, called Magnetars, which we just talked about, combine pulsar-like beams with staggeringly strong magnetic fields, creating some of the most powerful emissions in the universe. The energy in a pulsar beam is staggering. The Crab pulsar, left over from a supernova seen on Earth in 1054 CE, spins 30 times per second and emits so much energy that it powers an entire glowing nebula, visible across thousands of light years. Pulsars are also incredibly useful to astronomers. Their precise timing allows us to study gravity, test Einstein's theories, and even detect ripples in space-time from distant cosmic events. In a sense, they're like cosmic clocks, but clocks that could kill you if you got too close. What's unnerving is how many of them are out there. There are thought to be hundreds of millions of neutron stars in the Milky Way, many of them pulsars we simply haven't detected yet because their beams aren't pointed toward Earth. We're only seeing a tiny fraction of the lighthouses sweeping the galaxy. Pulsars are beautiful in their precision, but deadly in their nature. They are reminders that even the quietest parts of the night sky are filled with invisible beams of radiation, sweeping endlessly, indifferent to anything that might cross their path.
Collapsars. Some stars don't just die. They implode with such violence that they skip every other step and turn straight into a black hole. These events are called collapsars, and they are among the most catastrophic explosions in the universe. A collapsar begins with a massive star, much larger than our Sun, that has reached the end of its life. When it runs out of nuclear fuel, its core can no longer support the crushing weight of its own gravity. Normally, a star this massive would explode in a supernova and leave behind a neutron star. But in the case of a collapsar, the core collapse is so extreme that not even neutron degeneracy pressure, the force that usually props up a neutron star, can stop it. The core keeps collapsing until it forms a black hole.
This is not a quiet process. As the outer layers of the star fall inward, they form a swirling accretion disk around the newborn black hole. The disk heats up to incredible temperatures, and powerful jets of material are blasted outward at nearly the speed of light. These jets punch through the star's outer layers and shoot into space, creating some of the brightest explosions we've ever seen, long-duration gamma-ray bursts. A single collapsar can release as much energy in a matter of seconds as our Sun will produce over its entire 10 billion-year lifetime. If a collapsar's jets were ever aimed directly at Earth, the resulting gamma-ray burst could strip away our ozone layer and devastate life on the planet, even from thousands of light-years away. Fortunately, collapsars are rare, but they are also so powerful that we can detect them across billions of light-years, meaning we often see them as they were in the early universe. Collapsars are more than just cosmic fireworks. They are factories for heavy elements. The extreme conditions in the explosion forge many of the elements we find on Earth, including much of the oxygen we breathe and the iron in our blood. In a very real sense, we are made from the ashes of stars that died this way. But there's something haunting about a collapsar. The star doesn't just explode and fade away. It gives birth to something that will last virtually forever, a black hole, a point of no return in space. The light show is brief, but the remnant is eternal, silently waiting to swallow anything that comes near. Collapsars are a reminder that death in the universe is often spectacular and creative all at once. A single event can both destroy a star and seed the cosmos with the ingredients for new planets and life, even as it leaves behind one of the most fearsome objects in existence.
Supermassive black holes. At the heart of nearly every galaxy, including our own, lurks a monster. These are supermassive black holes, objects with masses ranging from millions to billions of times that of our Sun. They sit quietly most of the time, but when they feed, they become some of the brightest and most destructive objects in the universe. Our own galaxy, the Milky Way, has one, Sagittarius A*. It's about 4 million times the mass of the Sun and sits roughly 26,000 light-years away. For decades, we weren't even sure it existed. But astronomers tracked the orbits of nearby stars and saw them whipping around an invisible point at incredible speeds. The only explanation was a black hole that massive. Supermassive black holes are strange because we're still not entirely sure how they form. Stellar mass black holes form from the collapse of massive stars, but there's no single star big enough to collapse into something millions of times the Sun's mass. The leading theories suggest they formed from the direct collapse of enormous clouds of gas in the early universe, or they started small and grew by merging with other black holes and devouring everything nearby over billions of years. When matter falls toward a supermassive black hole, it doesn't just vanish quietly. It forms a spinning accretion disk,
heating up to millions of degrees and emitting intense radiation. This process can power quasars, which can outshine entire galaxies, and even launch jets of material thousands of light-years long. The scary part is how much influence these black holes have. They don't just sit in the center of galaxies, they help shape them. Their outbursts can regulate star formation, blow away gas, and even determine how big a galaxy can grow. In a sense, they act like galactic engines, controlling the life cycles of billions of stars. And they can grow. If a star or even a whole gas cloud gets too close, it can be torn apart in a tidal disruption event, with some of its matter swallowed and the rest flung outward at incredible speeds. These flares can briefly make an otherwise quiet galaxy blaze with X-rays and ultraviolet light. Perhaps most haunting of all is that supermassive black holes will be among the last objects left in the universe. Long after the stars have burned out, they will still sit at the centers of dead galaxies, slowly evaporating through Hawking radiation over unimaginable timescales. Supermassive black holes are terrifying because they combine two extremes. They are both invisible traps and some of the brightest, most energetic objects when they feed. They are the beating, or perhaps the devouring hearts of galaxies, shaping the universe while hiding in plain sight.
Quark stars. As extreme as neutron stars are, some physicists think there might be something even stranger. Stars made not of neutrons, but of their inner building blocks, quarks. These hypothetical objects are called Quark Stars, and if they exist, they would be some of the most exotic things in the universe. To understand quark stars, you have to start with a neutron star. A neutron star is essentially a giant ball of neutrons, atomic nuclei crushed so tightly that electrons and protons have fused together. But what happens if you squeeze even harder? At some point, the pressure could become so intense that the neutrons themselves break apart into their constituent particles, quarks. Instead of being locked together in triplets like they are in normal matter, the quarks would form a soup called quark-gluon plasma, or strange matter. If this happens, the entire star could turn into a single, uniform mass of quarks, creating an object even denser than a neutron star, but not quite a black hole. A quark star might be only about 10 kilometers across, but weigh more than the Sun, meaning it would be so dense that a teaspoon of its matter could weigh hundreds of millions of tons more than a teaspoon from a neutron star. Quark stars are still theoretical, but there are hints that some unusual cosmic objects might fit the bill. Astronomers have observed neutron stars that seem too small and too dense to be made of normal neutron matter. These could be quark stars, though we don't have direct proof yet. What makes quark stars truly eerie is their potential stability. If strange quark matter is more stable than normal matter, then it could be contagious in a sense. If a chunk of strange matter ever touched ordinary matter, it might convert it into more strange matter. That means a quark star could, in theory, act like a kind of cosmic seed, turning anything it touches into more quark matter. While this is mostly speculative, it's a nightmare scenario physicists have seriously considered. Quark stars would also have some bizarre physical properties. They might have a bare surface, no atmosphere at all, with quark matter exposed directly to space. Their light might look unusual, different from the radiation given off by ordinary neutron stars. If they spin rapidly, they could emit unique gravitational wave signals, giving us a way to detect them indirectly. Whether quark stars exist or not, they represent the next step in the chain of stellar collapse, a state of matter so dense and exotic that we've never been able to reproduce it in a lab. They are a glimpse into what happens when the universe pushes matter to its absolute limits. Quark stars are a reminder that there may still be objects out there stranger than anything we've seen, stars that aren't stars at all, but cosmic lumps of pure quark soup.
Neutron stars are already some of the strangest objects in the universe, but some physicists think there could be stars even weirder. These hypothetical objects are called boson stars, or sometimes boson stars, and they might be made of matter so exotic we've never seen it outside of a laboratory experiment. A Bose-Einstein star is thought to be made of particles called bosons, which behave very differently from normal matter. Most of the matter we interact with, protons, neutrons, electrons, are fermions, and they obey the Pauli exclusion principle, which keeps them from all crowding into the same quantum state. Bosons don't have that restriction. Under the right conditions, they can all collapse into the same state, forming something called a Bose-Einstein condensate, a kind of superatom where all the particles act as one. Physicists have actually created Bose-Einstein condensates in labs on Earth by cooling atoms to near absolute zero, and the results are bizarre. The atoms lose their individual identity and start behaving like a single, unified quantum object. Now imagine that happening on a cosmic scale. An entire star made of matter in this exotic state. A Bose-Einstein star would be incredibly dense, though perhaps not quite as dense as a neutron star. Instead of being supported by neutron degeneracy pressure like neutron stars, it would be held up by quantum effects in the boson field itself. These stars could be incredibly compact and dark, giving off little to no light. From a distance, they might look almost indistinguishable from black holes. Some theories suggest that Bose-Einstein stars could even explain certain puzzling observations, like gravitational wave signals that don't quite match what we'd expect from black hole mergers. If two boson stars collided, the resulting signal might look very similar, but not identical to a black hole collision. What makes these stars so eerie is how little we would know if we found one. A Bose-Einstein star wouldn't have a solid surface like a planet, or even a neutron star crust,
It would be more like a smooth, featureless ball of exotic quantum matter. If you could somehow touch it, you couldn't. The gravity would kill you instantly. You might just pass through layers of strange condensate that don't behave like any material we've ever encountered. Even stranger, some versions of the theory suggest these stars could form without any normal matter at all. Just pure bosonic fields collapsing under gravity. If that's true, there could be entire populations of these dark stars out there that we simply haven't noticed yet, hiding in the shadows where they barely interact with normal matter. Bose-Einstein stars remind us that the universe might still have surprises waiting. Stars that are neither normal stars, nor neutron stars, nor black holes, but something entirely different. Something that blurs the line between matter, energy, and pure quantum weirdness.
The Great Attractor. Right now, the entire Milky Way galaxy, along with our neighbors in the local group, is moving at over 600 kilometers per second toward something we can't fully see. This mysterious gravitational focal point is called the Great Attractor, and it's one of the strangest puzzles in large-scale astronomy. We discovered the Great Attractor by studying the cosmic microwave background, the afterglow of the Big Bang. When astronomers measured how our galaxy was moving relative to this cosmic backdrop, they found we weren't just drifting with the universe's expansion. We were being pulled in a particular direction, as if some enormous concentration of mass were tugging on us. The problem is that the Great Attractor lies in a part of the sky we can't see clearly, the zone of avoidance, where the dense plane of the Milky Way blocks our view with dust and stars. For decades, we had no idea what was actually there. Slowly, with radio and X-ray observations that can see through the dust, astronomers have mapped what lies in that direction. A massive region of galaxy clusters called Laniakea, which includes the Norma cluster and other huge structures. Even so, the Great Attractor is still unsettling. The name isn't just poetic. It really is pulling entire galaxies, including our own, toward it at incredible speed. And it's not just us. Thousands of other galaxies are moving in the same direction, as though all of them are falling toward some massive, invisible sink in space. Some scientists think the Great Attractor isn't a single object at all, but the combined gravitational influence of many galaxy clusters and dark matter filaments, part of the cosmic web. Others suggest that beyond the Great Attractor lies an even larger gravitational feature known as the Shapley supercluster, which might be the real driver of this flow. What makes this terrifying is the sheer scale of what we're talking about. We're not just moving towards something the size of a star or a black hole. We're talking about a region of space hundreds of millions of light years across, containing enough mass to drag entire superclusters of galaxies along with it. It's like watching ants being carried down a river, except we're the ants, and the river is the fabric of space itself. And here's the eerie part. We can't stop.
This motion isn't something we can control or even feel. It's simply the natural consequence of gravity on cosmic scales. Over billions of years, the Milky Way will keep drifting toward this massive region, slowly changing our place in the universe. The Great Attractor is a reminder that we are not stationary. The whole galaxy is on a one-way trip toward an unseen destination, pulled by something so massive that it bends the flow of galaxies across hundreds of millions of light years.
In the constellation Eridanus lies one of the most unsettling regions of the cosmos, a place so empty that it might be the largest void we've ever found. This is the Eridanus Supervoid, a vast region of space hundreds of millions of light-years across that appears almost completely devoid of galaxies. Astronomers discovered the Eridanus Supervoid while studying the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. When mapping the sky, they found a strange patch called the CMB cold spot, an area slightly cooler than the surrounding regions. To explain it, scientists began looking for something along our line of sight that could account for the temperature difference, and that's when they found the supervoid. The Eridanus Supervoid is estimated to be about 1.8 billion light-years across, making it one of the largest structures or anti-structures in the observable universe. For comparison, our entire Milky Way galaxy is just 100,000 light-years across. Inside this void, there are far fewer galaxies, stars, and clusters than in a typical patch of space that size. This emptiness is strange because the universe's large-scale structure is usually like a cosmic web. Galaxies cluster along filaments, with voids filling the spaces in between. But even the biggest normal voids are only a few hundred million light-years wide. The Eridanus Supervoid is far larger, and its sheer size has led some scientists to wonder whether it's just a statistical fluke or something truly unusual. Some cosmologists think this supervoid could explain the cold spot via the integrated Sachs-Wolf effect. Light from the CMB loses a little energy as it passes through underdense regions, making it look colder when it reaches us. But even this explanation doesn't fully account for how pronounced the cold spot is. That's led to more exotic theories, including the possibility that the cold spot could be a scar from a collision with another bubble universe during the early moments after the Big Bang. Standing inside the Eridanus Supervoid, if you could, would be unnerving. The night sky would still have stars, since they're in our own galaxy, but the deep sky view would look emptier. Galaxies would be fewer and farther between, and the nearest clusters would be unimaginably distant. It would be a place defined by absence, a cosmic desert stretching for billions of light-years.
Cosmic strings. Imagine a crack in the fabric of reality, not just in space, but in space-time itself, stretching across the universe like a fault line. This is the idea behind cosmic strings, hypothetical objects that might be relics from the very first fraction of a second after the Big Bang. If they exist, they could be some of the most powerful and dangerous structures in the cosmos. Cosmic strings aren't strings in the ordinary sense. They're thought to be incredibly thin, much narrower than a proton,
but so dense that a single kilometer of one could outweigh an entire planet. They might have formed as the universe cooled in the earliest moments of its existence, when fundamental forces were splitting apart from a unified state. Just as ice sometimes cracks when it freezes, space-time itself might have developed cracks or defects, leaving behind these infinitely long, ultra-dense lines of energy. Because they're so thin and so massive, cosmic strings would warp space-time around them, creating intense gravitational effects. If a cosmic string passed between you and a distant galaxy, you wouldn't see the galaxy disappear. You'd see its image split into two by gravitational lensing, as if space-time were bent like a funhouse mirror. But cosmic strings wouldn't just sit quietly. If two strings crossed and reconnected, they could release enormous bursts of energy in the form of gravitational waves, ripples in space-time that detectors like LIGO might one day be able to pick up. Some physicists think strange, unexplained bursts of radio waves or gamma rays could even be signals from cosmic string interactions. What makes them frightening is their potential destructive power. If a cosmic string were to pass through a planet, it would slice straight through without slowing down, leaving a trail of devastation in its wake. The gravitational forces near a string would be so intense that they could rip apart anything nearby. Fortunately, if cosmic strings exist, they seem to be incredibly rare, or so widely spaced that we haven't encountered one yet. Detecting a cosmic string would be a huge discovery. It would give us a direct glimpse into the physics of the early universe, possibly even energies far beyond what we can reach with particle accelerators. But it would also confirm that the universe is literally scarred, marked forever by relics from its violent birth. Cosmic strings are eerie because they're a reminder that space-time isn't just empty nothingness. It's something that can twist, bend, and even break. Somewhere out there, there could be cracks running across billions of light years, silent and invisible, waiting for us to find them.
Carrington event-level solar storms. In 1859, Earth was hit by the most powerful solar storm ever recorded, an event so intense that telegraph systems sparked and caught fire, and auroras were seen as far south as the Caribbean. This was the Carrington event, and if something like it happened today, it could plunge the modern world into chaos. The Carrington event began when a massive coronal mass ejection, a huge bubble of charged particles from the Sun, slammed into Earth's magnetic field. Normally, our magnetic field protects us from solar storms by deflecting most of the solar wind. But this CME was so powerful that it compressed the magnetosphere and flooded Earth's atmosphere with energy. The result was dazzling auroras and powerful geomagnetic storms that induced electric currents in telegraph wires worldwide. Back then, the world didn't depend on electronics. Telegraph operators reported sparks jumping from their equipment,
papers catching fire, and messages being sent even with the power supply disconnected. But society kept functioning. If the same thing happened now, the results would be catastrophic. A Carrington-class storm today could fry power grids, knocking out electricity across continents. Transformers could be damaged beyond repair, leaving some regions without power for weeks or even months. Satellites would be vulnerable to radiation damage, potentially disabling GPS, communications, and weather monitoring systems. Even airplanes could lose navigation systems, and astronauts on the International Space Station would have to seek shelter in shielded areas. The Internet itself could be severely disrupted. Undersea cables rely on repeaters that might fail under intense geomagnetic currents. Financial systems, which depend on precise timing from satellites, could go offline. Essentially, much of our modern technological infrastructure could be knocked back to a pre-electric age in a matter of hours. And solar storms like this aren't just a thing of the past. In 2012, a CME nearly as strong as the Carrington event missed Earth by just a few days. If the timing had been slightly different, we would have been hit head-on. NASA and other space agencies constantly monitor the Sun with spacecraft like SOHO and SDO to detect incoming storms. But even with warning, there would be little we could do to prevent the damage, only to shut down systems and hope to ride it out. Carrington-level storms are a reminder that space weather is not just an abstract idea. The Sun is a star, and like any star, it can unleash violent outbursts. Most of the time, Earth's magnetic shield keeps us safe. But when the Sun decides to throw a truly massive storm our way, all we can do is brace for impact.
Micrometeorites. Every single day, Earth is bombarded by space debris. Not giant killer asteroids, but tiny specks called micrometeorites. These are particles of dust and rock from comets, asteroids, and even other planets, and they rain down on us constantly. In fact, scientists estimate that tens of thousands of tons of micrometeorite material fall to Earth every year. Most of these particles are incredibly small, just a fraction of a millimeter across. When they hit our atmosphere, they burn up and create faint, invisible streaks of light, too small to see as meteors. By the time they reach the ground, they've cooled into tiny, spherical beads of rock and metal, sometimes found on rooftops, in polar ice, or even mixed into deep-sea sediments. On Earth, micrometeorites are harmless. Our thick atmosphere slows them down so thoroughly that they just settle to the surface like cosmic dust. You've probably touched micrometeorite particles without even knowing it. They're everywhere. But outside Earth's atmosphere, it's a very different story. In space,
Micrometeorites don't slow down. They zip around the solar system at tens of kilometers per second, faster than a speeding bullet. Even something the size of a grain of sand can punch a hole in a spacecraft if it hits at that speed. This is why spacecraft and satellites have protective shielding called Whipple shields, layers designed to absorb the energy of high-speed impacts. The International Space Station has been struck by micrometeorites countless times. Some windows show tiny pits where particles have slammed into them, and astronauts regularly inspect the station for damage. For space travelers, micrometeorites are a constant, invisible danger. In 2021, one even punctured a small hole in the Canadarm2 robotic arm on the ISS. Luckily, it didn't cause major damage, but it was a reminder that space is filled with high-speed shrapnel. A larger fragment could damage a spacesuit, a solar panel, or even critical systems on a ship. The Moon and other airless worlds take the full brunt of micrometeorite impacts. Over billions of years, their surfaces have been ground into fine dust by constant bombardment. If you ever walk on the Moon, every footprint you leave will eventually be softened by this steady rain of space grit. Micrometeorites are easy to forget about because they're invisible and mostly harmless here on Earth. But outside Earth's atmosphere, they're an ever-present threat. Tiny bullets flying silently in every direction. You wouldn't see them coming, and you wouldn't hear the impact. One strike in the wrong place could turn a quiet journey into a deadly emergency. They are a reminder that even in the emptiness of space, there's no such thing as complete safety. The universe is always moving, always throwing debris around, and we just happen to be in the crossfire.
Asteroid Apophis. In April 2029, a space rock named Apophis will give Earth one of the closest asteroid flybys ever observed, and it will be close enough to see with the naked eye. This 370-meter-wide asteroid will pass so near that it will actually come closer than many of our satellites. It's a rare, breathtaking event, and a reminder of just how vulnerable our planet can be. Apophis was discovered in 2004, and at first it caused quite a stir. Early calculations showed a small but worrying chance that it could actually collide with Earth in 2029. For a while, it was one of the most dangerous objects on NASA's risk list. Later observations ruled out an impact that year, but its close approach will still be extraordinary. On April 13, 2029, Apophis will sweep past at a distance of about 31,000 kilometers, or 19,000 miles, closer than the orbit of geosynchronous satellites. That means it will fly under the ring of communications satellites around our planet. For comparison, that's about 1/10 the distance to the Moon. For a rock that size, it's practically a cosmic near miss. If Apophis were to ever hit Earth, the results would be devastating. While it's not big enough to cause a global extinction like the asteroid that killed the dinosaurs,
It could still wipe out an entire city or region, depending on where it struck. The energy released would be equivalent to hundreds of megatons of TNT, far beyond the largest nuclear weapon ever detonated. Even though 2029 has been declared impact-free, scientists will be watching Apophis very closely. The flyby is so close that Earth's gravity will actually alter its path slightly. Astronomers want to measure that change to predict its future orbits with extreme precision, because there's still a small chance of an impact in later centuries. Not likely, but not impossible. For the public, the event will be both thrilling and unsettling. Apophis will be visible in the night sky over parts of Europe, Africa, and Asia, moving so quickly that you could watch it cross the sky in real time. For a moment, it will be one of the brightest objects in the sky, a reminder that Earth's neighborhood is not empty. Apophis also serves as a wake-up call for planetary defense. NASA and other space agencies are developing techniques to deflect dangerous asteroids, such as the DART mission, which successfully tested nudging an asteroid in 2022. Apophis is harmless this time, but there are countless other objects out there that we haven't discovered yet. The 2029 flyby will be an incredible scientific opportunity, but it's also a reminder that our planet moves through a shooting gallery of space rocks, and sometimes one comes just a little too close for comfort.
Comet Showers. Most of the time, comets are solitary visitors, coming from the distant reaches of the solar system on long, lonely orbits. But sometimes something far more dramatic happens. The solar system itself passes through a region of space filled with gravitational disturbances that can send thousands of comets tumbling inward all at once. These events are called comet showers, and they might have changed the course of life on Earth more than once. Comets mostly live in the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, extending trillions of kilometers into space. These icy objects are normally stable, orbiting quietly for billions of years. But every so often, the gravity of a passing star, a rogue planet, or even a dense molecular cloud can disturb the Oort cloud. That disturbance can fling swarms of comets toward the inner solar system. During a comet shower, Earth's skies might suddenly fill with bright comets, visible for months or even years. That might sound beautiful, but it's also dangerous. Comets are fast, much faster than most asteroids, and when they head toward the Sun, some of them can cross Earth's path. Even a single large comet impact could be catastrophic, triggering tsunamis, wildfires, and global cooling. A full comet shower increases those odds dramatically. There's evidence that this has happened before. Some scientists think past mass extinctions, including one about 35 million years ago, may have been linked to a spike in comet impacts, possibly triggered by a disturbance in the Oort cloud. Others have proposed that our solar system's slow orbit through the Milky Way causes periodic encounters with denser regions of space every 30 to 35 million years, leading to recurring comet showers. The scary part is that we wouldn't have much warning.
While we now track thousands of near-Earth asteroids, most long-period comets are only discovered months before they reach their closest point to the Sun. A large comet on a collision course might be spotted only shortly before impact, too late to mount a deflection mission. Even without impacts, a comet shower would be an awe-inspiring and eerie sight. Dozens of comets could appear in the sky at the same time, their tails stretching across the heavens. Ancient cultures might have seen such events as omens of doom, and in this case, they wouldn't have been wrong. Comet showers are a reminder that the solar system is not a quiet, unchanging place. It's influenced by the galaxy around it, and sometimes those influences can send icy missiles hurtling toward our planet. Somewhere out there, the next gravitational nudge is waiting, and when it comes, we might get a sky full of comets and a much higher risk of extinction-level impacts.
Lunar collapse theories. The Moon has always been a symbol of stability, the same face shining down on Earth for billions of years. But some scientists have speculated about a distant future where the Moon doesn't stay whole forever. According to certain lunar collapse theories, the Moon could one day break apart, forming a ring system around Earth. The idea comes from something called the Roche limit, which is the minimum distance an orbiting body can approach its planet before tidal forces tear it apart. Right now, the Moon is actually drifting away from Earth at about 3.8 centimeters per year thanks to tidal interactions. But far in the future, billions of years from now, that trend could reverse as Earth's rotation slows and the Moon's orbit becomes unstable. If the Moon ever started drifting back toward Earth, it could eventually cross the Roche limit, which lies roughly 18,000 kilometers, 11,000 miles, above Earth's surface. At that point, Earth's gravity would overwhelm the Moon's own gravity, pulling it apart into rubble. Instead of a single glowing disk in the night sky, we'd see a brilliant, shifting ring system, possibly wider and brighter than Saturn's. This scenario is far from certain, but simulations suggest that if it happened, the process would be spectacular and terrifying. The Moon might first crack into large fragments due to tidal stresses, creating multiple bright objects in the sky. As those pieces break down into smaller debris, they would spread out into a glowing band of dust and rock encircling the planet. For a time, Earth would be breathtaking to look at from space, but the aftermath could be dangerous. Lunar fragments would occasionally fall to Earth, causing meteor showers or even devastating impacts. Tidal forces would become chaotic as the ring system slowly lost material, possibly altering ocean tides dramatically and affecting Earth's climate. Some versions of this theory are even more dramatic, suggesting that if the Moon's orbit decays enough, it might not just break apart, it could spiral inward and collide with Earth, creating an apocalyptic event. That collision would release enough energy to remelt Earth's crust and turn the planet into a molten world before eventually cooling down. Most scientists agree that we don't have to worry about this anytime soon. It would take tens of billions of years, long after the Sun has expanded into a red giant and potentially engulfed Earth entirely. Still, the thought that the Moon could one day shatter into pieces and paint the sky with rings is both haunting and strangely beautiful. The moon feels eternal to us, but nothing in the universe lasts forever. Even our planet's silent companion might one day be torn apart, leaving behind not a comforting light in the night sky, but a ghostly, ringed reminder of what once was.
Earth's magnetic field flip. Earth's magnetic field is one of the planet's best defenses, a giant shield that deflects charged particles from the sun and cosmic rays from deep space. But this shield hasn't always looked the way it does today, and every few 100,000 years it does something dramatic. It flips. The North and South poles switch places, and during that process, Earth's protection could weaken for centuries. Scientists know this has happened many times before by studying magnetic minerals in ancient rocks. These minerals freeze into alignment with Earth's magnetic field when they form, preserving a record of its direction. The last full reversal happened about 780,000 years ago, and the evidence shows it can take anywhere from a few thousand years to as little as a few centuries to complete. During a reversal, the magnetic field doesn't disappear entirely, but it becomes weaker and much more chaotic. Instead of two simple poles, Earth might have several magnetic poles scattered around the globe, constantly moving and shifting. In the weakest phases, the field strength could drop to as low as 10% of its current level. That's where things get scary. A weaker magnetic field would mean less protection from solar and cosmic radiation. More charged particles could reach Earth's atmosphere, potentially increasing the radiation dose at the surface, especially near the equator. This could disrupt the ozone layer, allowing more harmful ultraviolet radiation from the sun to reach the ground. The effects on technology could be even worse. Our modern world relies on satellites, power grids, and communication systems that are vulnerable to solar storms. With a weakened magnetic field, geomagnetic storms like those caused by coronal mass ejections could become much more damaging, knocking out power on a global scale. Astronauts and high-altitude flights would be exposed to much higher radiation levels, making space travel riskier. There's also evidence that the magnetic field might already be weakening. The South Atlantic anomaly, a region where the field is much weaker than average, has been growing in recent decades. Some researchers think this could be a sign that a reversal is starting, or at least that Earth's magnetic field is entering a period of unusual instability. The good news is that life has survived dozens of these flips before, including our early human ancestors. There's no evidence that a magnetic reversal causes mass extinctions. But for our technological civilization, a centuries-long period of magnetic chaos could be a serious challenge. Earth's magnetic field flip is a reminder that even our planet's most reliable features aren't permanent. One day the compass will point south instead of north, and for a while our protective shield may falter, leaving us more exposed than at any time in human history.
Gamma-ray burst targeting Earth. Gamma-ray bursts, or GRBs, are the most powerful explosions in the known universe.
They are so bright that for a few seconds they can outshine every other star in their galaxy combined. Most happen billions of light years away, which is why we can safely observe them. But what if one happened close to home and aimed directly at Earth? A GRB is thought to occur when a massive star collapses into a black hole or neutron star, launching twin jets of energy and particles at nearly the speed of light. These jets are focused like cosmic death rays, which is why we only see a burst if one of the jets is pointed at us. There are also short-duration GRBs caused by the collision of neutron stars, events so energetic they warp space-time and send gravitational waves across the universe. If a long-duration GRB happened within a few thousand light-years and one of its jets was aimed at Earth, it wouldn't cause a fiery explosion on the ground. Instead, it would flood the upper atmosphere with intense gamma radiation, destroying much of the ozone layer in seconds.
Alien probes. In October 2017, astronomers detected something passing through our solar system that didn't come from here. It was named Oumuamua, a Hawaiian word meaning scout, and it was the first known interstellar object ever observed. But what made Oumuamua truly strange was how it behaved, enough to make some scientists wonder whether it might not be just a rock, but something far stranger. Oumuamua was unlike any comet or asteroid we'd ever seen. It had an unusual, elongated shape. Some estimates suggest it was up to 10 times longer than it was wide, more like a cigar or pancake than a typical space rock. It tumbled through space in a way that made its brightness flicker dramatically. And most bizarre of all, as it passed the sun, it sped up slightly, as if something was pushing on it, but without the visible tail of gas or dust that comets normally have when they outgas. Most scientists think Oumuamua's acceleration could have been caused by unusual outgassing we couldn't see, or perhaps by its odd shape acting like a solar sail. But others, including Harvard astronomer Avi Loeb, have suggested a more provocative idea. What if Oumuamua was artificial? A probe or debris from an alien civilization passing through our solar system? This isn't as far-fetched as it sounds. The galaxy is full of stars, planets, and possibly civilizations billions of years older than ours. If any of them launched probes to explore, some might eventually drift through other star systems. Oumuamua's speed and trajectory were consistent with an object that had been wandering interstellar space for a long time, perhaps millions of years, before crossing our path. What makes this idea eerie is that Oumuamua is now gone. It zipped past Earth and is on its way out of the solar system forever. We only had a few weeks to observe it, and we never got close enough to take detailed images.
That means we may never know what it really was. And then came Borisov, discovered in 2019, the second known interstellar visitor, this time a more normal comet. If we've already seen 2 such objects in just a few years, that suggests interstellar visitors might be more common than we thought. Who knows how many we've missed? The possibility that we're occasionally visited by alien technology, even derelict technology, is both thrilling and unnerving. Oumuamua may have been just a weird shard of rock or ice, but if it was something artificial, then we were briefly host to the work of another intelligence, and we didn't even have time to say hello.
Gray Goo Scenario. Among all the science fiction doomsday scenarios, few are as chilling or as plausible as the Gray Goo Scenario. It's the idea that self-replicating nanotechnology, once unleashed, could run out of control and consume the entire biosphere, turning Earth into a lifeless mass of microscopic machines. Here's how it works. Nanotechnology refers to machines built at the molecular scale, tiny robots that could assemble and disassemble matter atom by atom. In theory, such nanobots could be incredibly useful, repairing cells in the human body, building materials without waste, even cleaning up pollution. But if you give a machine the ability to replicate itself, to build more nanobots using raw material, you also create the possibility of a runaway chain reaction. The nightmare begins if something goes wrong with their programming. Instead of stopping when enough nanobots have been made, the system could just keep going, endlessly converting every available atom into more copies of itself. In this scenario, forests, oceans, animals, and even humans would just be raw material to be broken down and reassembled. The result would be a spreading mass of tiny swarming machines, the gray goo. This isn't just wild speculation. Scientists like Eric Drexler, one of the pioneers of nanotechnology, have warned about this possibility for decades. While we don't yet have the technology to build fully autonomous, self-replicating nanobots, advances in molecular engineering are getting closer every year. Researchers are already building simple nanoscale machines and even molecular assemblers that can perform basic tasks. What makes the gray goo scenario so terrifying is its speed. In theory, once self-replicating nanobots are loose, their growth could be exponential, doubling every few minutes or hours. Within days, they could overwhelm ecosystems. Within weeks or months, they might strip the surface of the planet bare. There would be no way to stop them once they reached a critical mass. Some researchers argued that such a scenario is unlikely because safeguards would be built into any nanotechnology, and uncontrolled replication would be inefficient compared to controlled, power-limited systems. But accidents happen, and malicious use is always a possibility. A rogue actor could theoretically create ecophagic nanobots, literally planet-eating, as a weapon or experiment, triggering an unstoppable catastrophe. The gray goo scenario is a reminder of how powerful technology could be, and how careful we need to be. Nanotechnology could cure disease, end scarcity, and revolutionize industry. But it could also, in the worst case, erase all life in a matter of weeks. If we ever unleash molecular machines capable of building themselves,
We'll need to ensure they're designed with absolute fail-safes, because once the goo starts spreading, there's no pulling the plug.
Proton decay. We tend to think of matter as permanent. Atoms are the building blocks of everything, from stars to planets to our own bodies. But, according to some theories, even the proton, one of the most stable particles in existence, might not last forever. If proton decay is real, then one day all matter in the universe could simply fall apart. A proton is a particle found in the nucleus of every atom, made of 3 quarks bound together by the strong nuclear force. As far as we can tell, protons are incredibly stable. Experiments have never observed one decay, and if it does happen, it's so rare that it must take at least 10 to the 34th years on average, far longer than the current age of the universe. But many theories of particle physics, including some versions of grand unified theories or GUTs, predict that protons are not truly eternal. They could very, very slowly break down into lighter particles, such as positrons and neutrinos. This would happen spontaneously, without any trigger. A proton could simply decide to decay, after waiting for a mind-bogglingly long time. The consequences are cosmic. If proton decay is real, it means that all matter is temporary. Over unimaginable timescales, atoms would fall apart, and everything made of matter, stars, planets, people, would eventually turn into a thin soup of radiation and subatomic particles. Even the most stable objects, like white dwarfs or iron cores, would simply disintegrate. This would mark the beginning of one of the final stages of the universe, the Degenerate Era, followed by the Dark Era. After black holes have evaporated through Hawking radiation and stars have long since gone dark, the last solid remnants of the cosmos would dissolve as protons decayed. The universe would slowly become completely empty. No structures, no matter, just radiation expanding forever. What's eerie about proton decay is that it's completely invisible to us now. If it happens, it's happening all around us, in some unfathomably tiny fraction of protons, without leaving a trace we can currently measure. Deep underground experiments, like Japan's Super Kamiokande, are actively looking for the rare telltale flashes of light that would indicate a single proton decay. But so far, no detections have been confirmed. If proton decay is ultimately discovered, it will confirm that even the building blocks of reality are not immune to time. It would mean that the universe truly has an expiration date, not just for stars and galaxies, but for matter itself. Proton decay is a quiet apocalypse, not a sudden catastrophe. It's the slow unraveling of everything, atom by atom, until nothing remains but a featureless void. It is the ultimate reminder that permanence is an illusion, and even the foundations of reality will one day crumble. Black Dwarf Era. When you look up at the night sky, every star you see is burning brightly. But that won't always be the case. In the far, far future, there will come a time when all the stars have burned out. The universe will enter what scientists call the Black Dwarf Era, a time when only the cold, dark remnants of stars will remain. Stars like our Sun shine because they fuse hydrogen into helium in their cores, releasing enormous amounts of energy. But they can't do this forever. Eventually, they run out of fuel. Smaller stars like red dwarfs will take trillions of years to burn out, while larger ones go faster. But given enough time, 10 to the 14th years or more, every star in every galaxy will use up its nuclear fuel and go dark. When a Sun-like star dies, it doesn't explode like a supernova. Instead, it sheds its outer layers, leaving behind a hot core called a white dwarf. These white dwarfs are incredibly dense, glowing embers of what were once shining stars. Over time, they slowly radiate their leftover heat into space, cooling down. Eventually, after an unimaginable span of time, much longer than the current age of the universe, these white dwarfs will cool so much that they no longer emit visible light. At this point, they become black dwarfs, cold, dead stars, invisible against the blackness of space. In the black dwarf era, the universe will be almost completely dark. Galaxies will still exist, but they'll be filled only with black dwarfs, neutron stars, black holes, and drifting planets. There will be no more starlight, no more warmth from fusion. The night sky as we know it will be gone, replaced by eternal darkness. But even this isn't the end of the story. Black dwarfs won't just sit there forever. Over incredibly long timescales, we're talking 10 to the 20th to 10 to the 25th years, quantum processes like proton decay, if it happens, could cause black dwarfs to slowly disintegrate into radiation. Some scientists have suggested that the most massive black dwarfs might even explode in extremely rare events called black dwarf supernovae. But this wouldn't happen until the universe is 10 to the 110th years old, a number so large it's nearly incomprehensible. For any hypothetical future observers, the black dwarf era would be a lonely time. The universe would be cold and almost completely still, with nothing new forming and very few sources of energy left. It would be a universe running on its last reserves, quiet, dark, and nearly empty. The black dwarf era is a haunting vision of the far future. It reminds us that starlight, something we take for granted, is temporary. One day, the last star will go out, and the cosmos will be left with only its cold, dead remnants, glowing no more.
Degenerate Era. The universe, as we know it, is still young, just 13.8 billion years old. But if we fast forward unimaginably far into the future, we reach a time astronomers call the Degenerate Era, an age when stars no longer shine, galaxies have gone dark, and only dead matter and black holes remain. This era begins after all the stars have burned out, billions of trillions of years from now. By then, every sun-like star will have become a white dwarf. Every massive star will have collapsed into a neutron star or black hole, and no new stars will be forming. The galaxies will still be there, but they will be ghostly and dim, lit only by the fading glow of cooling stellar corpses. In this time, the universe will be filled with what physicists call degenerate matter, white dwarfs, neutron stars, and brown dwarfs. These are the final, burned-out remains of normal stars,
held together by quantum forces rather than fusion. The last flickers of light will come from rare events like white dwarf collisions or the occasional radioactive decay deep inside dead stars, but these will be exceedingly rare. Planets that once orbited stars will continue to circle their cold remnants or drift away entirely, becoming rogue planets in the dark. Galaxies will remain gravitationally bound for a while, but over trillions of years, even they will begin to unravel as stars and remnants are slowly ejected by gravitational encounters. The Degenerate Era will also be a time when black holes dominate the cosmic landscape. Every galaxy will have a supermassive black hole at its center, and countless stellar mass black holes will wander the dark voids where stars once shone. Occasionally, two black holes will merge, sending ripples through space-time, the last dramatic events in an otherwise silent cosmos. But this era isn't truly eternal. Over unimaginable timescales, roughly 10 to the 30th to 10 to the 40th years, even these objects will begin to disappear. If proton decay is real, white dwarfs, neutron stars, and even planets will eventually disintegrate into radiation and subatomic particles, leaving behind only black holes and a thin soup of ghostly particles. It's a haunting vision, a universe with no light, no warmth, and no possibility of new stars or life. Time will still march forward, but nothing new will happen. The cosmos will be a graveyard of the objects that once shone, waiting for the next stage of cosmic history, the slow evaporation of black holes through Hawking radiation. The Degenerate Era is a reminder that everything has a lifespan, not only stars and galaxies, but the very processes that keep the universe vibrant. One day, all of it will fade into silence, and the night sky will truly go dark.
Black Hole Era. If we leap even further into the future, far past the death of stars and the silent Degenerate Era, we reach one of the final chapters of the cosmos, the Black Hole Era. This is the age when black holes become the last major structures in the universe, and even they are doomed to eventually fade away. Black holes are formed when massive stars collapse or when galaxies merge, leaving behind objects with gravity so strong that nothing, not even light, can escape. In the Black Hole Era, these will be the dominant objects left in the cosmos. All stars will be gone, all planets cold, all white dwarfs and neutron stars either decayed or ejected from their galaxies. The universe will be almost completely dark, except for the faint glow of particles colliding and the occasional flare when a black hole swallows some remaining debris. But even black holes are not forever. Thanks to Stephen Hawking's groundbreaking work, we know that black holes should very slowly lose mass over time by emitting Hawking radiation. This happens because of quantum effects near the event horizon. Virtual particle pairs pop into existence, and one of them escapes while the other falls in, stealing a tiny bit of the black hole's mass. For a stellar mass black hole, this process takes an almost inconceivable length of time, around 10 to the 67th years. For the supermassive black holes at the centers of galaxies, it takes far longer, up to 10 to the 100th years or more. But eventually, even the largest black holes will shrink, get hotter, and finally explode in a brilliant burst of radiation, releasing all of their remaining energy into the universe. After that final blaze, the cosmos will enter what's known as the Dark Era. At this point, there will be no stars, no black holes, and no large structures of any kind, just a thin soup of particles, photons, neutrinos, electrons, and positrons, endlessly expanding into infinite darkness. The black hole era is haunting because it represents the universe's last fireworks. For quadrillions upon quadrillions of years, black holes will be the only things shaping the cosmos, occasionally merging or devouring stray matter, sending out ripples of gravitational waves into the void. Then, one by one, they'll wink out of existence, leaving nothing behind. This is the ultimate fate of everything, the slow dissolution of the universe into nothing but radiation. Time will continue, but nothing meaningful will ever happen again. It's a future where not only stars and galaxies die, but the very concept of structure comes to an end. The black hole era reminds us that nothing in the universe is permanent. Even the most powerful objects we know, black holes, are only temporary features of a universe that is slowly, inevitably, running down toward eternal emptiness.
Big Rip. The universe is expanding, and not just expanding, but accelerating, thanks to the mysterious force we call dark energy. Right now, that expansion is gentle enough that galaxies, stars, and planets can remain gravitationally bound. But what if dark energy gets stronger over time? What if the expansion keeps accelerating faster and faster? This leads to one of the most terrifying cosmic scenarios ever proposed, the Big Rip. In the Big Rip model, dark energy doesn't just keep space expanding, it causes the expansion rate to grow without limit. Eventually, the outward push of space itself overcomes every force in the universe, one after the other. At first, distant galaxies would drift out of view as they accelerate away faster than light. Then, galaxy clusters, including our local group, will be pulled apart. But it wouldn't stop there. After billions of years, the expansion would reach the scale of individual galaxies, tearing the Milky Way apart. Stars would be separated from one another, drifting away into the ever-stretching void. Then, the expansion would overcome the gravity holding planets in orbit around stars, sending them flying off into darkness. And then it gets personal. As the Big Rip approaches its final moments, the force would become so strong that it would rip apart the planets themselves. A few minutes before the end, it would overcome the gravity holding Earth together, tearing it into pieces. A fraction of a second later, it would pull apart molecules, then atoms, and finally, even subatomic particles. Space itself will be stretched so violently that the very fabric of reality would tear. The timing of this ultimate catastrophe depends on how dark energy behaves. If its strength stays constant, the universe will expand forever, but never reach a big rip. But if its strength increases with time, something called phantom energy, then the big rip becomes inevitable. Some estimates suggest that if this were the case, the universe could end this way in about 22 billion years, long after all current stars have died, but still much sooner than the unimaginably slow heat death predicted by other models. What makes the Big Rip so eerie is its completeness. Unlike other cosmic endings, which leave behind dead stars, black holes, or cold matter, the Big Rip leaves nothing at all. There would be no survivors, no remnants, not even particles. The universe would be torn apart into pure, featureless space, with no structure remaining. It's the vision of total annihilation, not with a bang or a whimper, but with a final, unstoppable stretching that erases everything. If the Big Rip is our fate, the cosmos will die not in silence, but in the ultimate act of cosmic violence, where even the laws of physics themselves might be torn to shreds.